Is it working? Yes, it's working. So good afternoon to everyone. I hope that you have a nice lunch. So we're going to start this session, which is about the INSAR data products and services. So we have 4 or 5 presentations. I don't remember. All the speakers are there. So I think that we can start with the first presentation that will be given by is it Florian Provost from the University of Strasbourg, that will talk about the Timesat service. Oh, sorry, and I forget to present myself. I'm Nuno Miranda from the European Space Agency, and my co-chair,
José Manuel Delgado Blasco from REA Group.
Thank you very much. So my name is Florian Provost. I'm going to present you the service called Timesat, which is a service that aims at classifying large data sets of ground motion. So to start with some context, so there are currently more and more very large data set of ground motion products, such as the AGMS, but also nationwide processing that are done with different processing chain. And you have them in interferometry, but also with image correlation, such as the ETS Live that is monitoring globally the glacier. So those very large data sets present different challenges to exploit them and understand what they really contain and what are the relevant inside them. So to do that, we need to develop new tools to get rapid analysis and use HPC or cloud processing to do that. So for Timesat, so we were specifically interested on monitoring landslides. So this service was developed within the project, which was called EO for Alps landslides. And it aimed at providing EO Earth observation to new users that are interested on monitoring and modeling landslides. And we were interested at providing to such user a comprehensive interpretation of what was inside the time series and all the interferometric products. And for that, it was why deformation is important for landslides, is that it can characterize different, first it can help to detect them in a very large regional scale, and also it can, at local scale, help to understand what processes are going within them. So to do that, so the main goal of the service is to identify temporal and spatial cluster of homogeneous style of ground motion, and using different input data sets, which can be either discrete with point clouds, such as what we obtain with PS and DS in SAR, but also continuous with very large data cube. So the service includes different components with a preprocessing module that will detect outliers, smooth the time series. And then there is 2 modes, which is a supervised and unsupervised classification of the data of the time series. So the first mode is a supervised classification. So we worked with basically 5 different classes, which were predefined. So it's the uncorrelated classes. The linear one, where the trend, as you can see here, the time series is linear, and then there's a quadratic one, and then 3 different linear time series that are characterized by a breakpoint, which will be either continuous jump, and then we'll have the same velocity before or after the jump, or we'll have 2 different velocities before and after the jump. So the second mode is an unsupervised classification, which is quite basic and use the ECA-PCA decomposition and provide the first component of the principal component decomposition or the independent component analysis. So basically, technically one of the main challenge was to be able to process a large amount of data. So we actually designed the service so it could be run on optimized data cubes and use ride optimization to really be able to process the data cube from the different dimension of the data cubes, and then like maximize the processing rapidity or speed. So then this service is available within the EO4Apps landslide application. So it's an application that is available on the geohazard exploitation platform, and it's available among different services that you can see here that gather like offset tracking, optical offset tracking, but also interferometric services, and also here the Timesat that is post-processing that can ingest the output of the previous service as I mentioned. So services were available for a large amount of users in the alpine environment, in the European Alps. So they could get access to this Earth observation and get access to some training to understand better how to use remote sensing processing. So how to run the service? So first you have to select the service on the web page. Then you can like select your output from another service or any kind of data cube you want to ingest and drop it on the menu on the right, and then select and tune the parameters that you want to define and run the service. Once you've done that, you also can have access to a tutorial that is available on the same website. And finally, one of the first output you get is a PDF which gathers the different characteristics of your output, such as how many points were classified in the different classes, and also the PCR, how they look in the time series. I will now present like 3 different sites that we tested the service on, which is the Valais Canton in Switzerland, the Mont Blanc Massif in France, and the Briançonnais in France as well. So to start with the last one. So here are the results. So here you can see on the left the velocity, the mean velocity over the region, and you can see that you can observe some unstable slopes that are moving at different speed. And here on the upper left, on the right, you have the supervised output and then the 3 first PC principal component decomposition. And you can see that depending on the principal component of, you are looking at, you will see different sites having a strong weight or not. If you look in more detail, maybe not. Yeah, this is one. So that's a zoom on the 3 precedent area I was showing. So here you have the velocity and the result of the supervised classification, where you see that around the landslide you also have like similar classes than within the landslide, and then the 3 first principal components of the decomposition, and you can see that they have different features especially. If you are more interested on the supervised mode, we provide also like the breaking point, for example, the breaking point occurrence. And here you can see that on the last landslide I was showing, you have like all of them are classified in the same class, which is a bilinear behavior with a jump and 2 different velocities. And you can see that the jump occurred in beginning of 2016 with a quite large velocity magnitude difference before and after the jump. Then on the other side, so it looks like that. So you get the velocity. Here it's a supervised result with the different classes, and then the PCA. And here again, if you try to zoom on one of the landslide, you will get this kind of the same behavior with a gathered class with a breaking point that is occurring in 2018 this time, but with a velocity change that is much lower. The final test was done very recently, so it's very preliminary results. That's the output of offset tracking with Sentinel-2 over the Mont Blanc glaciers in the Alps. And you can see here the mean velocities that you obtain if you process all the Sentinel-2 acquisition from 2016 to 2023. So you can see in the east-west and north-south component, you see different glacier moving. We just processed
welcome to the first afternoon session, to the ionosphere and the atmospheric session. We have started a little bit late because of delays with the lunch. And welcome everybody. And so my name is Falk Amelung. My co-chair is Giovanni Nico.
Yeah.
And there are my glasses.
Maybe I can read for you. The first presenter is Felipe Betancourt-Pavan, who is going to present a work. The title is Two Words and Interferometric Autofocus for Ionospheric Phase Signatures in Biomass. You have 20 minutes, 3 minutes before I will give you the time.
Thank you.
So you get both of them at the same time.
Yeah, you hear me well? Yeah. So welcome to my presentation of today, which is like building the path towards the interferometric autofocus for the ionospheric signatures in biomass. I'm going to, wait, can I? Okay, now. So I'm going to speak about a bit about biomass and about the ionospheric errors. Then I'm going to describe a method for the calibration of the, no, for the, a method for the characterization.
It's really on the session live, yes.
Yeah, it's live.
It's live, the live of the other session.
Should be. Should be called something that YouTube here.
All right. So some conclusion and perspective. Basically, this service is still like under test and still like in development, but we are we would be very happy to have tester and feedback. If you are interested, you can try it for free. And yeah, we are delivering to the point currently like many information, and we still have to work on how to provide them in a more intelligible way. And yeah, we are thinking of several updates and developments in the future. Thank you very much for your attention.
Are there any questions?
Maybe I can speak first.
I don't know, the other side maybe don't will hear you.
Thank you very much for your nice presentation. It's difficult. To use the Timesat tool, you need to process the satellite image in JEP, or you can do it.
No, we actually, you can either process it on JEP and use the output of the services on JEP, but you can also use EGMS outputs, and we'll try to fit those format already.
And if I have my own
yes, you
results.
can upload it on JEP and then use a service. So you will have a data storage, you can upload your results and then use a service.
Okay.
Any question?
No, not yet. It's just very simple at the moment, but that's what we are aiming in the future. All right. Thank you.
Questions?
Sorry.
Yes.
Yeah, thanks for the talk and thanks for soldiering through all the technical issues. Yeah, I was just wondering, because you focus on landslides, have you got any hopes to apply that to sort of any other types of hazards or any other deformation signals?
It was developed especially for landslide because it's an application that was not really tested with those kind of techniques so far. So we wanted to, other groups did it also this year, so we were in this movement. But as you could see, like we tried it on Glacier, so to see if the service is like applying to different cases or not. So yeah.
Great, thank you.
Thank you.
Thank you very much. Go to the next speaker, David Becker. We'll talk about Opera analysis, Redisar, and optical products.
Thank you very much. First of all, I'm very excited to be back in Leeds. I see a lot of familiar faces. I did my PhD here, and after I left, I haven't come back since then. So it has been 7 years, and I need to say not much has changed on campus, and somehow that's reassuring and exciting to see all those familiar faces again. But meanwhile, I'm going to go and give you an overview of the Opera project, as well as the different products that we are producing from SAR and optical data sets, and specifically its surface water, surface disturbance, surface displacement, but also a couple of key intermediate products like an radiometric terrain corrected product and a core-registered SLC stack product. So this effort that I'm presenting here, I am the Opera project manager, but I couldn't have done anything here without the whole team. So there's a large team behind it. You will see that in the subsequent slides. But it's also not a single institution. We are working together with many different partners to realize this. So the background and how this really came to existence is the vision of Gerald, who is sitting over there. And he has always wanted to have generated these global products. So there was a mechanism that came to an existence, which is through the Satellite Needs Working Group. These are federal agencies that express needs, remote sensing needs, and then NASA is doing an assessment and recommending certain products. Now that is the opportunity for through Congress to get funding for implementing these products. And Opera is really funded out of the 2018 cycle. So there's these 3 products that I mentioned here before. And on the right-hand side, you can kind of see all of our different institutions that we're working together with, which includes universities like GLAD, which is the University of Maryland, University of Alaska, Fairbanks, as well as Cedar Methodist University. Then we have consortiums like EarthScope, which was formerly called UNAFCO, and other partners from NASA like Goddard. Let me see if this is working. No. Oh, there we go. So in terms of the team, really, if we put all the people together, we're a group of 60 plus people, and it can be ranging of people working 20% or full-time on it. And this is just the collection of faces that send their photograph in. There is many more. But just to kind of stress that this is really a large undertaking of a broad team, and it ranges from scientists, it ranges from algorithm developers, computer scientists, system engineers, etc. Not to mention the business office, of course, as well. I will just cycle through the different products and give key characteristics. So the first one is the surface water extent product. We will be mapping this from harmonized Sentinel and Landsat data. So that's Sentinel-2 and Landsat-8. Then we also have Sentinel-1, A and B, as well as NISAR. And unfortunately, SWAT has been removed due to funding constraints, so that one is delayed, as is marked at the bottom, until further notice. But really, by having these different satellites all together, you start looking at surface water extent at a very rapid revisit time every couple of days, 2 days or so. And we're generating this product on a near global scope, and the product has been operationally, or has been in production at least for the optical component since April of last year. So you can go and find these products already on the DAC website, so the Data Active Archive of NASA. For water products, that's a physical oceanography DAC called PODAC. So go and check it out. And then in future, we have different staggered releases, as I will show you in the next slide. You will have the Sentinel-1 that gets added, and then subsequently NISAR. Then we have the surface disturbance product. This one is mapping vegetation changes as well as spectral changes. Again, optical data, but recently it has been added to our scope to also produce the SAR-related component from Sentinel-1 for this product. Again, this is a near global product at 30 meters, telling if your pixel has been disturbed with respect to a historical baseline. The optical product has also already been in operations, and this product is freely available again, but distributed through the Land Processes DAC, which is LPDAC. Now we go to more perhaps the products here of interest to this group is the displacement product. So you have the European ground deformation map. I'm happy that this is kind of the vision where we're going to also have a counterpart for North America. So this is a line of sight displacement product from Sentinel as well as from NISAR. Will be generated for every pass that there is data. So the cadence really depends on the 6, 12 days or 24 days depending on the sampling. It's better than 30 meters. It's a full PSDS product. And I will show you a derived example afterwards. But we are also looking at the full historical extent of the mission. So it's not a forward stream product only. So it goes back to, let's say, when the Sentinel-1 data became more stable and around the beginning of 2015. This product distributed by the SAR DAC, which you're all familiar with, is the ASF DAC. And lastly, I want to make note of a notional product. It's not yet funded. But it has been proposed by NASA to OMB and Congress, is the generation of a decomposed product, so a vertical land motion product. And that would be currently only from Sentinel-1. So if that product is realized, you are really starting to have a counterpart with respect to the European ground deformation, but then for the North America geographical scope. Then there are two intermediate products, radiometric terrain corrected product, or the RTC product. This is only for Sentinel-1. NISAR mission has its own product, which is called the GCOF product. But this product, we're currently in our validation phase and wrapping that up. It is to go into production about 1 month from today. It's a forward stream product, again, 30 meters. And then we have the core-registered SLC stack product. That's for Sentinel-1 and NISAR. Again, the Sentinel variant is to go operation in 1 month from now. And that, as core registration says, it just resampled to a common grid. And this will be for Sentinel-1 a burst-wise product. And then for NISAR, it's going to be a frame-based product. So here is the timeline that I was talking about staggered releases. We're really trying to get the algorithms matured, implemented, and get them out to the users as soon as possible. So the top row is what we have already realized. We are in operational production for those. And then you can see the second row, Sentinel-1, RTC, and CSLC products. They're coming up, starting production next month. And then what you can also see the next row under the kind of the products that are coming down in the years to come. You can't see here yet the SAR disturbance product. We still need to add that up to it. You can also see the NISAR launch date that is currently planned. And you can see that the NISAR related products hence come a little bit after the NISAR launch, so we can use the validated and calibrated products of NISAR. So I'm kind of giving you some of these snapshots of these different products. So here is the dynamic surface water extent product. For the optical one, you see that these are multiple satellites combined. This is the Landsat 8, then the Sentinel-2A and the Sentinel-2B. And what we're doing is we're classifying whether a pixel has open water, so fully water, partial water, mixed classes, or has no water at all. So that is labeled over here in that. And this animation is just a 1 month snapshot of the products. Again, available, so if you follow that QR code, that's where you can go ahead and download the products. Now, the key thing is that we can go ahead and start complementing this with the SAR data once it becomes available. So the algorithm team led by Haresh, who's also sitting in the back, has been developing this, and we are maturing that for Sentinel-1. So here you can see the example of the optical, where you have cloud cover as a main limitation, and then complemented by the SAR, where you can, of course, penetrate through it, and you also have a little bit of sensitivity to inundated vegetation, etc. So really what we expect here for Sentinel-1 versus what we will have with NISAR is that for NISAR, we will definitely be mapping all the wetlands. For Sentinel-1, we are committed to do it in the herbaceous wetlands. Going down to the surface disturbance that we have again here. This is for the optical data. So we had recently a lot of fires in Canada, impacting much of the North American continent, and here you can see the burn scarp extent. Again, like I said before, this is a time series derived product with respect to a temporal baseline. So we're trying to get rid of the interannual variations. And that product is also pretty well suited, given that it does vegetation and spectral changes for urbanization, landslide mapping, etc. The key thing is we're not adding any sort of attribution to the change. That's what we would expect that the user would do himself, being the expert for that area. Again, this will be complemented with a SAR-derived product in the future from Sentinel-1. Then the surface displacement product, if it wants to pop up. Oh, there we go. But I think I might have skipped a couple of slides. So no, I was mistaken. So the next one over was the RTC product. So here is a snapshot of as we have produced the data in our current processing system for the globe. The RTC is going to be again available in the next month from now, and you can see on the right-hand side an example of what it does. It really removes the impact of the topography, highlighting some of the changes that otherwise or some of the features that you otherwise would not be able to see, like urbanization, thinking about forested slope, glaciers, etc. So we are going to be using this as an intermediate product for our water product, as well as the displacement product, the disturbance product. Okay, then we have the CSLC stack product. As I said, we have the North America geographical scope, which is kind of shown over here. This product is co-registered, corrections already applied, so you can just do cross multiplication to go to interferometry, or you can start thinking about on-demand coherence change, etc. Again, next month this product will be available, and I would encourage people to go to Haresh's talk in the other room after mine, where he will give more of an overview of the ETAT corrections as well as the algorithm background. Then here, the displacement product, this is going to be frame-based, again, line of sight. This is further out, a year from now, can be used for tectonics, subsidence, generally whatever everybody's doing in the room, it should be suitable for that from an INSAR perspective. I wanted to talk a little bit about the notionable product. Here I kind of showed an example on how it could look like when we derive it. Really, we take away the relative nature of the INSAR, the ascending and descending, and move it towards a mosaic product. There is going to be a poster tomorrow from Marin, where he's going to give more details about this product in specific, and how it could be looking like for Opera. Then okay, so then I wanted to again talk about the data access. Everything is free and open at the different DACs. So this is the links for the water product as well as the land disturbance product. If we go towards the SAR DAC, which is LP DAC, they have their own product page, which is the Vertex page, which is shown over here. Again, they provide value-added services that many of you are familiar with already, and that will be similar for the RTC and the CSLC product. There is also the Earth data page, which generally where NASA have all of their data sets. You can search just for Opera and find the products there that are currently available, and the future products will be there as well. So, and then I'm going to show one more slide here on data access and discovery, which is the visualization. So I showed you that imagery where the products come in, and you can see the footprints go over time. RTC products will be there as well, which are mosaic, so you can start looking at animations and global analysis relatively straightforward through that service, and it's called Worldview. And lastly, I wanted to kind of talk about the different resources. We are also committed to be full, open, transparent, and reproducible. So all our code is in the open domain for people to play with, reproduce the products, and even the system is there. So I invite you to go and have a look. And lastly, we are always looking for input from others. So we have working groups. There are already a lot of our European partners participating in. But if you're interested in providing feedback, either on the products or using some of the early products, please join us on our mailing list or shoot us an email for any ways on how you can engage. Thank you.
Thank you, David. Very impressive presentation. Is there any questions for David? Perfect on time.
Okay. Good.
Yeah, maybe Anna.
I was just wondering if you have compared your products with some of the other available data sets. So, for example, the surface deformation, is it effectively similar to the Comet Lixar type thing, or are there differences?
Yeah, so we're currently prototyping based on a lot of the area products. I mean, they're pretty similar to the Lix products. For Opera itself, we are changing the way on how we're processing. It's not pair by pair processing, it's a full time series approach from persistent scatterer and distributed scatterer. So we are expecting differences, and I mean, our expectation is it would be better from the conventional pair by pair processing.
Just a very quick question before we move to the next speaker. So you are generating this geocode SLC. Are you using it for generating the displacement product?
Yeah, it's our intermediate product for going to displacement, and we thought it would be a very valuable product because you don't need to do the co-registration anymore. You kind of cut away a lot of the processing. Hence, NASA was willing to make that available to the community and archive that.
Right. Thank you very much.
Thank you. And if people want to have some stick posters or like bookmarks, I put it here. It gives a summary of each of the different products, so it might be easy on the plane.
So we move to the next speaker. The presentation will not be given by Francesca Casu, it will be given by Fernando. And we talk about how spaceborne and airborne INSAR products can support the civilian protection.
Okay, good afternoon, everyone. My name is Fernando Monterroso. I come from Irea CNR in Naples, Italy, and Dusuro. And now I will basically present the different automatic tools that we are developing for monitoring the seismic ranges and also volcanic areas in Italy and other parts of the world. So this is my presentation. I need to wait here. Okay. Already you know we developed in the operational service to EPOSAR. There is an automatic generation of seismic displacement maps that we generate more or less 5 years ago. This is the big catalog of the different DINSAR products for different big earthquakes or significant earthquakes around the world. So basically this automatic tool is put in function and now supervised in an automated way DINSAR products for scientific community, specifically for the Air Civil Protection Department. In this case, we developed these automatic tools to put all our data in EPOSAR service, TC, and also the hazard exploitation platform. This is the BIESA. So already we are processing more or less the 605 earthquakes around the world with more or less 45,000 products with interference and loss displacement maps and also coherence maps. We can check here the EQ for check with our information, and this is obviously respect to the standard available of data of the EPOSAR data. So we can check here. This is the web page of your portal when you get access to the visit and check on our data. With this case, recently I brought this occasion for show you the different seismic interference from Morocco earthquake with the past Saturday. We can see here the seismic interference of the above the both interferometric pairs, the 12 days and also 24 days for Sentinel-1. And also the lost displacement maps. All these products already available in a post job portal. So the next generation about this automatic tool is the pre-operational automatic source modeling by using the EPOSAR products. We are developing with colleagues and Simone Azzori from National Institute of Geological and Volcanology in Italy. We are put all our catalogs to develop in an automatic way the source modeling. In this case, we are developing the fault solutions for different earthquakes. More or less, we take about the 100 earthquakes. These results are put in and also in the future in our catalog. We are working now in the metadata. If you are interested about this research, we talk about the next Thursday for more details specifically for this automatic tool that we work in developing now. You can check and also the QD paper that we are publishing recently. So this is in concern with earthquakes, specifically we have the monitoring earthquakes around the world with different earthquake magnitudes with 4.0 to 4.5 for European area, specifically for Italian territory. And for the rest of the world, we are show you that we are processing more or less earthquakes with different magnitudes and different significant earthquakes around the world. So we talk about to do volcanic areas. In this case, we create an also non-supervised way the operational service to run the information monitoring of the Italian volcanic volcanic areas, specifically to support the Department of Civil Protection in Italy with the seismic crisis of volcanic eruption crisis. In this case, we developing the automatic mode, the generation of the products. Using the Sentinel-1 images, we create this automatic tool and also to generate in wave mode the loss displacement velocity maps and also the combination. So basically, we are using all the satellite images as Bible finds 2015 for the both orbits. In this case, this example is for the Napoli Bay area. We can see here the track, ascending and descending track. We are using then also the algorithm developed in IREA CNR. In this case, we are using the PS-BUS algorithm. This is Manunta 2018. That basically is this algorithm is adapted to processing the Sentinel-1 images to interferometric way. So we generate the loss and velocity maps for the both orbits, and after we combine this information to generate the time series. This is the information that we basically use to create a report, let me say, to support the civil protection for every month that we need, we perform the meeting to report about the different seismic areas in Italy. Every time there is a new acquisition for Sentinel-1, for example, if we participate in 1 month in one meeting, so we process more or less 3 satellite images and the coordinate more. So in this case, we add the satellite images to add to the loss deformation velocity maps, ascending and descending for the create the combination, we say the vertical and horizontal displacement maps. So basically, now I will show you some results. We can see here the Campo Ferrei caldera, the most beautiful place around the world. In this case, this caldera, obviously, you can know that the Campo Ferrei is an upfleet, more or less the 1 meter in the last 15 years. So this is an example for the Campo Ferrei caldera. We are processing more or less 400 images, the Sentinel-1, B and A, so now just 1A. And we are processing more or less in the total of 11 and 86 interferometric pairs. So this is an example for Campo Ferrei caldera. We can see here and also the trash of the line that basically across all the city, we can see the up in the center of the Pozzuoli Square in the Naples. That represent more or less the deformation of the 1 meter in the last 15 years. So the next case is the Etna volcano. It's another significantly important volcano in the south of Italy, specifically in Sicily. In this case, we can see here more or less the deformation pattern in the area of the volcano. But since 2008 and the end of 2008, we can see experiment this jump above the earthquake with Fandiaka fault for 4.8 magnitude. So we can see here this jump that occurs in this volcano. So every month, obviously, we support the civil protection to report, which is the behavior of this volcano in the south of Italy. The other case is the volcano Iceland. We can see here the other interested cases. In these cases, we are processing the same amount of images for the both orbits to generate the loss deformation velocity maps, and also to combination the vertical and horizontal displacement maps for in this case of the volcano Iceland, of the Eolie Iceland in the south of Italy. For this case, we are see you here at this unrest that occurred in the last 2 years ago in the area of on the crater of the volcano. We can see here more or less the unrest that occurs in the September, November in 2021 and different area of the volcano. So basically, for this volcano, we are submitting the paper for understand what happened when it unrest in the area of the crater volcano. So we can check in the future, maybe we don't check this paper because now in this phase submit. The other cases is the area of Stromboli volcano. We can see here the Iceland. It is of course in this big volcano in the area of the Stromboli. We can see here the same deformation pattern in the time series for the ascending and descending orbit. In this case, we can see here this small deformation pattern in the area, change deformation pattern in the area of the in the year of 2019, and after the other small change of the pattern in the end in the autumn in 2022. So specifically for this case, we are we are working in the group, in IREA CNR group, with the pre-operational service to airborne SAR system, specifically to create the airborne X-band interference SAR. We are working with the static antenna in this area for the study of the Sciara del Fuoco in this area. This is a volcano on the Stromboli volcano. So we are created on the single pass interference to generate a digital elevation model. In this case, we can see here which is the different the 8 October in 2022. So, which is the conclusion of the future perspectives about these kind of activities we can monitoring and support the civil protection department in Italy to create different results to earthquakes. In this case, we are now development. We need to be operational system. We need to be operational group to create the operational EPOSAR service. In this case, standardized products available through EPOSAR infrastructure. Support, obviously, during the civil protection department in Italy or in other areas of the world that are interested to check this information. During the seismic crisis, for example, now in the Morocco earthquake, we create now the interference, and now, in this moment, it's supposed to maybe is available now the automatic modeling of the slip motion of the area of earthquake. So basically, we are pre-operational automatic seismic source modeling. That the next Thursday I will speak along this topic. And about the volcano monitoring, we are satellite. We have satellite operational system that maybe we can create. We can update the different loss deformation velocity maps and loss time series in the area of interest of different volcanoes in Italy, in the south of Italy specifically. And an airborne system, and also we are working with pre-operational airborne sound system to monitoring and with more details in this area. Continues to support to the civil protection department during the crisis. So the next challenge is analysis and interpretation of measurements. Specifically, we are developing and also artificial intelligence to understand which is the technical interpreted analysis to this data, and moves to airborne system operational practice and the next constellations that we are waiting for to present the next results. So this is all. Thank you very much. This is my Twitter. I'm active in Twitter when I put all the information. So if you have questions.
Any question? No? I will fire one. So I understand that you have a really operational services with a clear clients identified there, or clear customers identified behind your service, which is sorry. I understand that you have a very operational service here. Yes. With customers well identified, being the civil protection. So could you tell me what was the impact of the loss of Sentinel-1B into your services?
Oh, the impact is really interesting. So even to the seismic crisis, do you know, to Italy has more or less 5 volcanoes in constantly activity. So every time the past week we have experimented in Naples, specifically the earthquake, more or less the magnitude 3.9. We need to create in automatic way these results to be operational and to respond with emergencies, specifically in this case of events. Obviously, we talk about the Etna volcano. Every month we create more or less, we adjust in our system more or less 3 images. So we need to be attend to do available images to create two different maps, and also because we need to attend to different meetings to show that our results, and these results we can take on different decisions about to do behavior of volcanoes. Yep.
What's the resolution of your seismic data you're using?
What is the resolution?
Of your seismic data you're getting?
Oh, okay. The resolution of the results of in this case is 20 meters.
20 meters.
Yes.
So anything below 20 meters you cannot detect, correct?
Yeah. Okay. Is another question?
Another question? Don't be shy.
Don't forget that the next Thursday we can talk about to do automatic modeling. That is the next generation of the next step of the automatic tool of earthquakes, the Sentinel-1 products. Okay. So thank you very much. Okay.
Thank you very much.
We move to our next speaker, Michael Fumelis. They will talk about the nationwide Sentinel-1 PSI surface motion of Greece using on-demand snapping service and JEP.
Hi, good afternoon. My name is Michael Fumelis. I'm coming from the Aristotle University of Thessaloniki. Now I'm showing you like another operational service. There are a lot, which means that we are quite mature to reach the level of having services and not like discussing still the processing. I will show you an implementation that was done on the geohazard exploitation platform. It's called snapping. And I will show you an effort to do a user-based production at a national level. So the difference with the previous presentation is that a user is processing himself. He can produce the product himself on a platform compared to the other services where you find like a data-ready, analysis-ready products. So I'm coming from the University of Thessaloniki, as I said. We are a small group working on Earth observation and geohazards. We are trying to collect everyone who's working in the university in a common umbrella to have, we have built what we call Center of Earth Observation and Ocean. And this is to gain the advantages of multidisciplinarity between the team. Next slide, I don't think, why it's moving too fast. I can do it backwards. So I don't think I need to show you this slide. Everyone knows here SAR, and there are several people that did that even before me. So we will focus on the persistent scatter analysis for this talk. This is an initial version of the tool that we developed together with Jose Manuel using the ESA Snap toolbox and the stamps developed by Andy. This slide shows you what was the situation back in 2012 before the Sentinels were launched. Everyone was awaiting that we will be bombarded with a large data set, and we want to go to this operational stage processing, and we need to deal with all of this big data analysis. And at the point, a lot of people already from here were at this time in Santorini in Greece, and they proposed that it's good to have like a system okay. A system will take advantage and process automatically all this data set, and I think that was the initial part that ESA thought of the exploitation platforms, and JEP is one of them. JEP is focusing more on the geohazards. So there was a need from the community, in fact, and this was built. One of the solutions was JEP. Okay, this is the JEP interface. In fact, if you go today here, there is a post about the recent earthquake in Morocco, so you can find the interferogram as well. And this is what we did. We took the ESA Snap toolbox, which is a powerful tool. It's not only for education. And the PSI processing that was developed, stamps that was developed by Andy. And we tried to optimize that in a processing chain to implement it on the platform. So we have also the idea of not to avoid reprocessing everything from scratch once the new acquisition is made. So we split our processing into two. Snapping IFG, which is just to generate all the interferograms and store them in the platform. And then on top of that, you just run the PSI later on, and you have the time series solution. So each time that you have a new acquisition, you can generate the interferogram, store it there, and depending when you want to have the PSI solution, every one acquisition, every month, every 3 months, you can update the solution. This is saving a lot of resources and time for the processing. And this storage is stored locally on the platform for future use. So this is the idea. The services as we build them was the snapping PSI medium resolution and full resolution. The only difference is that we are merging the point scatterers at the medium resolution to have lighter product. So the idea was just to have the medium resolution one, which is able to run over very wide areas. And then if there is a signal, interesting signal, you can focus later on with the full resolution one. The PSI, the PSDS, PSI Plus we call it, it's not integrated on JEP. It's something that we will do in the future. This is, right now, we are processing locally at the university. Then this is the interface of the services. So this is the IFG, PSI full and PSI medium. You have user-defined parameters. Here we need to decide where to go, because real experts want a lot of processing parameters to control and produce, but non-AO experts, they just want like really the basic. They want just to click on a few buttons and get the results. So we find out like the medium solution to provide, at least to ensure that even if a non-expert run this one, will end up with a robust results and not an erroneous one. So this is the IFG one, you run it. These services are being integrated. The operational one is running a year now. This version, another version was like 4 years ago. And it's being developed and upgraded all the time. So this is an example of what we get. This is the airport of Thessaloniki. This is the medium resolution one. It's 100 meters per pixel. And this is the full resolution. And this is the time series that you can get from that. Now, in terms of outputs, you have the PSI outputs, you have the normal one, code, latitude, longitude, all the time series, some specific columns of interest. And there are several products that you can get from the processing. One is the CSV with the time series, shape files, some browse products. And finally, we have added recently this HTML code, which is, was requested by users. And this is a simple file, a file that you can open with any internet browser, and you can browse the measurements. And this is nice because you don't need like a super sophisticated geospatial tool to see. It's a way to check the results quite quickly. This is initial work that we did over the Nile Delta. And we generated, that was the first time, in fact, that we tried a wide area processing. And the idea is that we had a platform that has some capabilities. And until now, we were processing small areas around the world, local parts. So the idea was to just try to use the system to see its capabilities. So that's why we went to the Greek, to process the entire Greece. To do that, we figure out that it would be better not to process the entire frames, but to split them into tiles. This is to avoid also some propagation of error at the corners. So we split the area into 54 tiles, 90 by 90 kilometers approximately, and we ensure to have like 10 kilometers coverage from all the sides. This is just to have all this information in case that we want in the future to merge all the data set to put it in the common frame. We process from 15 until 2021, all the entire archive. And this is the result. That was announced. The processing was, in fact, completed last year in September. We announced it somewhere in Christmas that we will put all this result on JEP. The story is that the platform was not ready to have a new visualization tool. So we decided to wait until this visualization tool comes. This is the frames that you see that we process, like it's 6 tracks, around 4,000 SLCs, 4 million points at medium resolution. And an example over a small area. In fact, this is the area where currently we have the major floods in Greece. And we receive a lot of questions whether this flooding will cause like acceleration of motion there or something. A lot of people are asking. So this is the visualization product that I received yesterday from JEP. So we integrated everything on the platform. All this visualization is based on the very nice concept that the Norwegian did in the Norwegian ground motion service. It was an excellent browser of the data to check the time series. Don't worry about the colors because they didn't tune nicely the colors. It was fixed by 4 plus and minus 4 millimeters per year. So this is a very nice map, in fact, to cause panic in Greece and start. So I will I will avoid interpreting that. So remember this one. It's much better. It's greener. So this is operational. This will be open. It is open to public right now. So if you go to the JEP and you have only registered, you don't need to pay anything. You don't need anything. You can go to this area here under GMS, because also on JEP they have integrated all the GMS, EGMS products, and you can use this. These products are really nice because also you can do validation between the different measurements and so on. And again, I'm saying that these ones you can even produce yourself. The advantage here is that if you have this data set there, and if you want a specific tile, you want to update this specific tile, you can go and update the interference of this specific tile and rerun the PSI and have the solution. You can have the medium res, the full res, so you can do whatever you want using this data. And of course, you can download the data and use it as they are. So here comes the question of the verification and validation of the products. In that step, we didn't go to the validation with other geodetic techniques. So we said verification, and we verified our measurements with an independent tool, which is also integrated on the geohazard exploitation platform. It's the PSBus from the group of Cenerea in Italy, in Naples. So what we did is we run snapping, we run PS bus. This is the difference for the common points, and you see that there is a consistency between the products. We did that not only in Haiti, but I did it in Thessaloniki because this is the area that I'm living now. So you see that there is a consistency. Of course, there are deviation between, slight deviation about the techniques, but in general, they are consistent. And consistency also is shown not only in the velocity, but also in the time series. So more or less, we are getting the same time series. I'm not picking the best ones just to show that like it's really consistent. But it is, this is important, very important, because till now, when we talk with non-expert, they're a bit reluctant on using or exploiting the data. They think about the accuracy and so on. At least I think once you have two services where users can run them themselves and they can see that they can get the same results, and even compare with EGMS, I will show some slides later on, this gives more credibility to the entire techniques and so on. So this is also the case over Surabaya in Indonesia. This is snapping and SBAS. So the techniques are different. The processing is completely different. So you can see also here, you can grab this bridge, which is not here. But so this is the points which are not common, are not within 100-meter pixels a distance between them. So you see that PS bus, as expected, you can extract more information, more spatial information about the product. This is normal, but still PSI is performing quite well, and it's also grabbing some man-made structures. So this bridge here. Now we are working on updating also the height in the interferometric processing, just to ensure that these points will fall exactly on top of the bridge. So also this is another validation for a moderate earthquake. I know that PSI is not optimum for processing of earthquakes, but this is really slight motion. What we did, we run PS bus on JEP in IFG mode, so interferogram. So this is on the left side, the interferogram, and we extracted this exactly from the jump that we see from the time series of SNAP, and you see that the results are more or less consistent. Another thing that we work all for this verification thing is, as expected, to use also EGMS to see how if you are doing well or not. So EGMS now, you have the specific products for the specific geometry that we used also here to generate the grease results. So this is the EGMS, the one from snapping. If you go also to the full resolution, you see that it's more closer to this one because this is run at full resolution. And if you check the time series over a point here, which is the most deforming one, you will see that it's not that the velocity field is consistent, but also that the time series show very high level of consistency. Once we saw that, we realized something else, that we have other seasonal signal that you can see here, or a bit more noisy compared to the EGMS. So we thought that there is also a filtering procedure applied to the EGMS. And surprisingly, when we were checking these results and the consistency between this data set in an area, in most of the cases in Greece, it was fine. But once you are checking that in areas where you have an earthquake, this is there is a deviation in the results. So what you see, for instance, over this point here from the two data sets, is that here they are really smooth, and the effect of the earthquake is not considered. So the jump caused by the earthquake is kindly, not only temporarily, but not only spatially, but also temporally smooth. So this can cause some problems sometimes in the interpretation of the results. I'm sure that I'm not saying that EGMS is bad. I mean, this is an excellent, really excellent product, but maybe in the cases of earthquake, it requires a bit more hands-on to remove this effect, which is more something can be done here. In the filtering procedure that you can apply also in snapping, you can avoid that. So here also snapping medium resolution for the earthquake in Tirnavos. It was 2021, and so you can see here over the area that is more affected. These are the consistent results between the two data sets. You see that more or less, I didn't apply any calibration between references and so on, but the results, the patterns are exactly the same. And the time series, as I told you just before, they're a bit different. So here you see the jump of the earthquake and some seasonal pattern because it's an area which is also a lot of groundwater variability there, which these ones you don't see that in this specific time series. But this is only in the case of the earthquakes. Apart from that, there is a consistency between the data. What we are doing with these data sets, and we are doing other geometries, so on, is to focus on the deformation for each of the cities, extract some nice graphs, and see the amount of population affected for each city by potential ground motion. So this is some different examples from areas in Greece, in big cities in Greece. In fact, these are the cities that we had also the land cover from the ESA land cover atlas. Okay, so here I need also to how this was done. That was done by the support of ESA. Of course, you are running something on the platform, but you need the resources to run all this stuff behind. So we did that with the support of the ESA Network of Resources initiative. In fact, everyone that wants to use these services, not only this one, but other ones that are on JEP, they can use this initiative to get the funding for the processing, and they can get the results from. This is I'm done. Thank you very much for hearing.
Thank you, Michael. Any question? You have some minutes still for a question.
We are 10 minutes ahead schedule, so you have to say 10 minutes on the grill.
I can go back.
You can dance, you can do some Greek dance, or what? Can you do some? Now, is there any question for Michaelis?
Yeah. Just one question. I'm wondering if, for example, big infrastructure people like harbors or whatever are using your data and what for, and can they use their data, or are they keen to use your data?
The question is if they can or they are keen to use it, because it's different.
Let me say if they are keen to use it, yes.
I think with the EGMS, that was like a real push to the community to see that what we can do and what we can extract from the data. There's complementarity because with EGMS you have like fixed processing. It has the advantages and disadvantages. If you show them also that you can go on a specific site, do something else more detailed and local stuff, and you are consistent, I think they'll start using it, yes.
Thank you.
Yeah. But not showing the map with the red dots, it will not.
Another question?
Yes. John.
Thanks, Michael. I'm just wondering how you managed to capture multiple wavelengths of a jump in a time series on your earthquake examples.
The jump, you mean? We were cutting the processing. So we were running the processing as it is, but in the step of the filtering procedure, we were not filtering like the entire time series, but we knew exactly the time of the earthquake. This is not easy to be done in an operational service for entire Europe. So here I was controlling the processing myself.
And then how did you
You see the jump, but as we know from the PSI, I'm not sure that this jump is the entire motion of the earthquake. At least you avoid showing like something which is smoothed like before and after, because what's happening is that most people start asking, was there a signal before the earthquake that we didn't notice? It was going down before. So you just avoid this kind of question. I'm not saying that doing that for an earthquake would be the best chance. Even if EGMS will find a way to custom this case for the earthquakes, the jump of the earthquake might be underestimated by PSI. But no special processing was done for that.
So there's something that I like pretty much in your presentation, which is the fact that you have been able to show the difference between two different processings, or two different processings, and trying to use that as a way to validate or verify your processing. And I think that we have seen that, and maybe that's more a question for the seed questions. We have now a number of platform or services that are providing similar type of information with different type of processing. But in the end, it's always the same thing. If the way to access this information is totally different. So if a user wants to access the data from the platform A or from the platform B, it has to really to apply a different way of accessing the data. So since we are talking about the same type of signal, would you recommend that those people try to work together in try to have a harmonized way to access this information, such that it becomes a bit more transparent and easy to get processing or to get time series from different platforms, different processings, and merge them together in order to verify or to get more confidence on the processing?
I'm sure that we need really to merge all the data from different providers, because it's good to have several people running different algorithms and doing different things, because I'm sure a group doing much more than what we do, others do differently. The only thing that we need to ensure, and this is coming even from what I saw before, I was running something which is more or less automatic. I'm using the generator chain was also automatic. I was not trying to do anything. I was comparing with data sets which were published from other groups with other algorithms, and they were showing consistency. So I would say, depending on the algorithm and the location, you can use one performs better than the other, but at least a message would be that we are now at a good stage to maturity to say that more or less we should get the same results. So, but you can never stop other people, like ASF is doing like also very nice time series and so on. So.
Thank you. I think that we can move to the next speaker. Thank you very much, Michaelis.
Now, next speaker, Giulia Tessari, will show us a land motion monitoring service of Switzerland.
So good afternoon, everyone. I'm Giulia Tessari. I'm working at SARMAP, a Swiss company. And I'm presenting here the implementation of the deformation service over Switzerland. So just to give a context, you saw already many times this European ground motion service. Unfortunately, Switzerland is not part of Copernicus, so the Swiss Confederation tried to cover, let's say, this gap and to implement a similar service over Switzerland. And so the company I'm working with was in charge to do it. The results I'm going to show, and what I'm going to show, is mostly the implementation of the service, as the results are not published yet. So I'm not focusing on analyzing what we could detect, but more what were the main challenges, as Switzerland is actually a pretty complex environment. Okay, so the area we were working with over was Switzerland plus Liechtenstein, and a buffer 5 kilometers all around Switzerland, so a territory of roughly 50,000 square kilometers. And I don't want to do a touristic advertisement, but everything that is a beauty for Switzerland is actually a challenge for who is processing SAR data. So really high peaks, glaciers, glacier lakes with mountains, everything is green. You know, Switzerland is known for the greenery all around and nice forest. So you for sure know what I'm talking about. I don't need to explain why it is a challenge, but actually like 60% of Switzerland is covered by Alps. Is like 13% of the Alps are actually located in Switzerland. We have 30% of forest that I don't have numbers about the snow cover that is recently changing pretty fast. But we have peaks of more than 4,000 kilometers. So 4,000 meters, sorry. So just to say that I think it was making sense in this case not to run everything automatically, but to spend a lot of time trying to tune the parameters to see what was the best way to extract the best possible information over this area. So we were working over 5 different tracks, 2 ascending and 3 descending. The first part of what I present here is from the starting of Sentinel-1 mission up to November 2022. So it was about 400 scene per track. Obviously, we are going on with the updates, with yearly updates. So here you see the mosaic of the ascending and descending. And here is the coverage of the tracks. This is another challenge we were facing. So when Sentinel-1 mission started the first year, the acquisition were not really regular. So you see like these timelines where I show some gaps on the acquisition. From the technical point of view, the best choice would have been just to cut everything before November 2015 and start with a sort of continuous acquisition, series of acquisition. But obviously, when you have a tender and requirements, you need to respect the requirements. So we needed to ingest all the available scene. That could somehow create problem, you know, when you process multi-temporal analysis, having long temporal gaps is for sure an issue. You can also notice here we were somehow preserving some overlap between the tracks. That was part of the quality control I will discuss later. So I'm not spending much time on the algorithms because you perfectly know what are PS and this bus. So we were asked to provide both persistent scatters and distributed scatters, as is the status of the art for any service. Our approach that we call enhanced S-bus was basically processing the S-bus and preserving the low pass components, so the displacement, time series, and elevation, somehow to initialize the PS and to retrieve and to preserve the high frequency temporal components of the time series and extract the PS later. Here is basically the same. I'm just highlighting that from this processing chain, we extracted different kind of products that are somehow in line with what the European Ground Motion Service was also requesting. I will give more detail about the products. But just to know that there was obviously a part of the process is automatic. So the ingestion of Sentinel data every time we have new scenes. So what could be automatized is automatic. But obviously tuning the parameter and some decision on the processing implementation were actually requiring a lot of human discussion and intervention. If you want more details about the algorithm, we have a poster tomorrow that is also comparing this, what I call enhanced S-bus with an enhanced PS. So we also have another multi-temporal approach that is still providing PS and DS. This is the description of the products. We were required to provide all our results in tiles with a grid of time kilometers, time kilometers, sorry, as requested by Swiss Topo. That is actually the institute that is supervising this project and our contact point. So we provided both shapefile and GDB geodatabase, both slant range results so SAR geometry, line of sight deformation, geocoded products, and also the combination of ascending and descending in a raster grid. This is one of the big challenges if you work in mountainous areas, so atmosphere. To try to reduce the atmospheric artifacts, as if you try to process data as they are, all the Alps are moving, so everything is moving. So we try to reduce as much as possible the atmospheric components, exploiting the GACOS platform. So we were using the tropospheric GACOS correction provided by the Newcastle University. This is obviously not enough because of the resolution of this data. So we were also running as an additional phase eye correction screen, trying to be careful because obviously the size of the window is really tricky. Like the risk is to remove some real movement. So we are working with a pretty large phase eye correlation windows. And then finally, we were also exploiting the multitemporal component of the high pass and low pass filter of S-bus and PS. Obviously, we could correct a lot of artifacts due to atmosphere. Still, it was not completely removed, and I mean, expert eyes can still see it. The other big challenge was the snow cover, because I mean, most of the area is Alps, but still we have some like plains, some cities, so it's not that all Switzerland is always covered by snow. There are some seasonal period with snow, and depending on the elevation, snow is affecting the country in different ways. So here is an example what the EGMS is doing. So there is no a common approach, obviously, because every country has different issues. In the Alps, you can see that they were somehow preserving a continuous time series. You will probably notice it's a bit more noisy with a sort of seasonality, so probably when it's snowing. While for example, Norway, they decided to mask out all the snow period because it was more homogeneous, let's say the temporal snow interval. I mean, there is no right or wrong, it's just a choice. So in our case, because we were in a situation in between the two, we decided to apply a selective mask that was working only over some period of the year and only over some elevation. So our results will show some continuous time series where in the plain or over Zurich, Bern, over the urban areas, and the Alps or part of the Alps over a certain elevation are somehow masked to avoid some misleading information that could be extracted during the dry snow period. And obviously, I mean, the melting and snowfall are already somehow automatically losing information because of the correlation, but we have some coherent period with snow that somehow are providing misleading results. So we were just masking over some elevation to avoid to compare like the ground and the dry snow periods. Then there were a lot of quality controls as it was requested by the tender, obviously. So we got GNSS point. We had to verify the quality of the atmospheric correction through some short interferogram variograms to see how the correction was working. We needed to guarantee point density based on the land cover plus consistency on the overlapping areas. So the controls where we try again to automatize as much as possible, but obviously some calibration was needed. I just show you some of the quality controls we ran. So I show you before the overlapping among tracks, but also among bursts. So we were somehow verifying on the overlapping area, the consistency of the mean velocity, and we got to a mean difference of less than 1 millimeter per year and the standard deviation less than 2 millimeter per year, while the comparison with GPS that were stable points was really small in terms of mean velocity, so less than 0.2 millimeter per year with a standard deviation almost 3 millimeter per year. And this is another layer that we were asked to generate, so the density map. And again, this is somehow always tricky to guarantee the quality of what you provide, but the density as well, because we know there are some areas where there are the correlation. There are areas with fast movement that go beyond the capability of the technique to measure this displacement. But obviously, we need to find the best compromise between the point density and the quality of the points we were providing. I just go back, because, maybe no here. Okay. So we reached the point where we generated all the historical displacement. We also work in the first year update and working now in the second year update. The resolution of the product is, let's say, the best resolution in case of PS, 5 meters times 15 meters, while for DS we got a 30 meters times 30 meters resolution. Some interesting things that we were asked to provide was the percentage or the number of the real, the image that were really used, the interferogram that were really used in every time series. And in case a point was somehow a part of the time series was interpolated, this information was provided. Because who is using the data, finally? Want to know if it's something the SAR is doing, something that is coming from our interpolation. So we had additional field date by date stating if this was a measured point or interpolated point. And yeah, so to conclude, this is what we reach up to now. So creating this historical analysis from 2015 up to 2021, then the first year update. And there is another year update that is due. Obviously, we verify the capability of measuring slow deformation trends. Still, there are a lot of really fast landslides where there are ground truth, and we verify we were not able to describe this fast motion as well as glacier, and it was not a request actually, so permanent snow was fully masked. So the idea of providing anyway a service at national scale is not completely substituting the local scale and like specific case study of landslide or so. There are still something that both in terms of temporal updates that in terms of tuning of parameters cannot really be fully described by a national scale service, at least in our experience over Switzerland. So thank you for your attention.
Do you have any question?
Well, there, and then Harish.
Yeah, sorry if you said it already, but maybe I missed it. Who is using your data at the end? Like,
Sorry?
Who is using your data? I mean, for who do you provide data?
Swiss Topo, so the Swiss Confederation was paying this service, and Swiss Topo, that is the National Institute of Geology.
I got that, yeah, but for who at the end? I mean, do you think for
if they
who
decide
wants
to publish the results, they will be open to, for sure, the research institute and possibly to the public.
Okay,
but it's
but
not
as you
our
said,
decision.
For research, maybe like local studies are better. Because are you precise enough to give good data, like for landslide, for example, or you think you have the accuracy to give good data for landslide, or?
Yeah, I mean, this is one of the parameters that is included in the metadata.
Thanks.
Thank you.
Thanks for the presentation. I was wondering for the masking, at the end, how are you doing it? Basically, are you using ancillary data?
No, I mean, it was one of the options, even trust coherence, but it is becoming a second process, like creating mask day by day. So we were somehow verifying the last decades, the behavior of snow when it was snowing, and we did for a few years, we did some analysis both on optical and coherence data. And we decided to mask everything from 1,500 meters up from November to April, and thinking that before and after the coherence should do its work. Like, because if there was snow is melting or if it's snowing, everything else is going to be masked by the coherence. Obviously, it's not super fine. It could be better, but still, when you work at national scale, it's already a compromise. Better than masking everything or preserving noise or errors.
Thanks. And just a comment on your verification across different subswats.
Yeah.
Well, I think, do you expect that always be consistent? Because I wouldn't, basically. I just have a comment.
Yeah, let's say that we were using some calibration points in the overlapping areas. So the reference point we use for calibration, then the final product was calibrated on GPS or part of GPS we got. But there were some previous internal calibration.
Okay, so just to be clear, basically, the incidence angle is different from this subswat.
Sure.
So the same signal could be different.
Yeah, sure, but it's still like Sentinel is not having a huge angle from SWAT to SWAT. It's just a small variation. And it's still, I mean, we were accepting an error. It was not completely the same.
More questions? No? Just one comment on your, one of the first slides you mentioned that there were a data gap 2015. And I think that it was my fault actually at the time.
No. I think from up to Milan to Italy, there are data.
I think
the
that
frame after that is missed.
At the time, we were having a lot of problems with radiometric calibration, and our transponders were located in Germany close to the LR. So we need to acquire diversity of modes and polarizations that create the gap that you are probably actually seeing.
I mean, I think it's normal when a mission is starting, so we were not complaining.
So is there any more questions for Julia? Yes.
When analyzing such extreme topography or some terrain like in Switzerland, you learn a lot about problems in your processing because they show up in this terrain. So did you learn anything for the rest of Europe to better process this data?
Oh, I mean, okay, Alps are covering already a big part of Europe, so I think some challenges are there. Oh, I mean, I now present this. We used to work all over the world, so it's not that we just work over Switzerland over here. So for sure, one other issue that is, again, a big discussion, recent discussion with moisture over fields. So this is another big topic that is here, but everywhere in Europe for sure. Then, yeah, I can go through many problems. So every time I process data, there is something that should be considered. So at the same time, I think it depends from the accuracy you want to get. There are some errors that you can tolerate, like atmosphere. I mean, every time you need to tune atmospheric artifacts, depending where you're working on. Sometimes it's not an issue at all. Sometimes, depending on the sensor you're using, is changing the issue. So it's still not something that is fully solved, but depends on the scale of displacement you're analyzing. If the artifact is bigger than displacement, then you need to somehow take care of what is going on.
More questions?
So if there is no more questions, I'd like to thank all the speakers and the audience for this session and for all the good questions. Thank you very much. We have the coffee break now, and we start in 30 minutes or 40 minutes from now. Thank you very much.
Yeah, thank you.
Sorry, I'm Jean-Philippe Mallet. I'm from CNRS Strasbourg in France.
And the first talk is, the program is not fully correct. So the first talk is on the SNAP microwave toolbox by Michael Fumelis from the University of Thessaloniki. You're on, Michael.
Yes. Hi again. So now I will show you some developments on the SNAP microwave tool of ESA. In fact, I have joined the team quite recently today. The presentation was not prepared by me, and so I will try my best. Let's start. So I don't know how many of you have used SNAP in the past. Can you raise your hands? Maybe it's nice. So all of you. So I'm not sure if I will tell you more things than that you already know. So I'm using also SNAP, and this is not only for academic educational purpose with the students, but we, as I showed in the previous session, we are using it operationally for snapping toolbox on JEP. So it's a powerful tool. I believe it's open source, which is great. So, as I said, it's one of the freely available open tools of ESA for performing several interferometric processing. Not only about, 1 second, apologies. Not only Sentinel-1, but it is a mixture of operation for Sentinel-1, 2, and 3, plus other missions, other third-party mission and other. So it is a suite of tools that you can use. The advantage is that it is scalable to run also notebooks for large data production. And it tries to include some cross-cutting edge operators. In my own development, we are also integrating it on cloud resources, and it performs quite stable. So right now we are at the base of 1 million downloads, over than 1 million downloads, and 10,000 registered users on the forum, which means there are people who are using it actually and trying to have answers to their needs. And you can see the cumulative downloads here for a different version of the tool. Either it is Windows, Linux, and so on. I think most of the people are using it. If you are using only for 2 pairs of images or 1 single pair of Sentinel-2, so on, you can still use it on your own PC. But definitely, if you go to a step of processing multiple time series and so on, I don't know that if a single PC or local server can deal with that. And anyway, so in June 2023, this tool was renovated. At the end of this year, we are expecting support of other ESA mission, but we will go to these details later on. And from the end of the next year, it will support also NISAR, Biomass, and other time series tools, but I think there are a few slides for that later on. Just to introduce the actual developing team. So it's Brockman Consult in Germany, Skywatch in Canada, and there is CS in France and Romania. This is, of course, with the support of ESA. The Aristotle University of Thessaloniki is included in the project as more consultant. So Snap Desktop. So I'll show you different things inside Snap. I'm sure that many of you, since everyone was raising its hand, have seen things like that. It's the visualization capability. So you can not only visualize Earth observation data, but you can also visualize some auxiliary data, land cover maps, or Earth digital elevation models, and so on. So, and based on this data, you can either generate RGB, different kind of RGB automatically, so the system recognizes what kind of mission you are and adapts all the generation of the code and recognition of of the tool, of the operator based on each mission. To be honest, I was processing also with other kind of software, but for instance, if you have an image and you don't know where the image is located, you just have a zip file in your PC. For me, it is a great tool. You put it inside, it gives you the geolocation of the footprint. And also there are other tools inside that, like the one here, which is kind of library. So if you launch it, it scans your entire PC, grabs all the Earth observation products inside your PC, lists them, and you can do searches on that, and you don't need to go to each subfolder. You can use this data and store them locally and so on. So this is great capability. I don't know how many of you are using the product library. And of course, you have also a bunch of tools for data analysis, profiling, histogram, comparing the spectrum of different images and so on. In terms of processing, there is a different way to execute an operator. I think, as also we are doing with the students, you go first with a simple operator in the GUI. So you just go, select some images, go step by step on some products. The disadvantage of this procedure is that you have stored on your local PC all the intermediate products. So you run an operator, you save it, you run another one as an input to this one that you had already, and so on. And this is causing like kind of especially when you are having to deal with a lot of time series, takes a lot of time. Another advantage for the data processing part is, especially when it comes to the Sentinel-1 product, is that it reads already the zip file. This is not, I haven't seen that in other kind of software, which means that you just drop the zip file inside the tool and start using the product. In all the other softwares that I have used, usually you have to unzip the file, which means that you have double size product in your PC and so on. Still, when you have one pair to do or a couple of images, it's fine. But when you have like 300 scenes, SLC, this is like really a problem. This is even saving time when you do the processing on platform infrastructure, because there someone needs to pay for the computational power, and this makes a huge difference. Then, apart from that, you have the idea of building a chain of tools, which is the graph builder. So instead of running each of the operators separately and save each time the product from here, you have this graph, what we call it, and you don't have intermediate products, and you go and you save the last one. Of course, you can put right in all intermediate products that you need, but this is a very important way to process without storing things on your PC, intermediate products. Then you can go from very simple graphs like that to a very complicated ones. Now, although this seems very sophisticated and wow, it can generate millions of things for you, I would not recommend to go directly like that. The idea is that if you do like split one image into 3 subswath and merge them in the same time, usually this causes delays in the execution. So what you would do, in principle, you will just go in one split, you will go in this one procedure for one subswath, and then you can execute again for different subswath and so on. So there are different ways to execute a graph, and also you can execute it within the GUI interface, but you can have the graph and execute it in a Linux interface with GPT. So you can just use already processing chains like the graph and execute them, and this is in fact the way how we execute the snapping IFG on the JEP platform. Okay, again, we have this, I can go back. So here are a few examples from Sentinel-2, normalized water indexes. This is a hot topic right now in Greece, where we have severe floods in entire country. This is a nice mosaic over Ireland using 16 scenes. It is a composite of backscatter coherence. And we go now to the SAR functionalities. So more or less, I think that all the operators that you would need to execute SAR processing or in-SAR, the in-SAR processing are available within the toolbox. And this does not only apply for strip map data, but also for TopSAR. So this is quite important. Another very important advantage of the tool is, by the way, I'm not advertising because just to advertise, but it is something that if you have deal with processing, you will understand the problems. For instance, automatic DMs. If I decide right now to process on Morocco, I need to go to fetch the data of the DM over Morocco, stitch them, prepare them in the format of the specific software in order to use them. And I should do exactly the same for orbits, which means that I need to go to the repository, download the orbits, either they are precise or restituted orbits, and put them in my processing. Here, these two steps are fully automatic. So you can download multiple datasets, DM datasets automatically. It will recognize the area of your image. It will recognize the dates. It will download automatically from the repositories the orbits, the DMs, use them inside the processing and so on. Even if you decide later on to call some land cover products or whatever, there are also automatic way inside that you click and the land cover product comes for this specific area inside different kind of product. So, I mean, there are a lot of things which are easing the execution of the processing. Now, quite important is the integration of Snap with other software, which is the Pulsar Pro, to do some polarimetric analysis. The polarimetric analysis done, there are several operators inside Snap to do polarimetric analysis, but the more sophisticated one on Pulsar Pro, you can reach them because the two software talk to each other. Then there is this integration with stamps and P-rate, which means that you can prepare the interferograms for the time series analysis. And this is what we are doing on JEP. In fact, we are preparing all the processing, the interferograms. We are exporting them in stamps specific format, and then we are using them for post-processing. And there is some open source software that we developed also with Jose Manuel to automatically called Snap to Stamps. So it is a chain that uses all this operator of Snap to generate automatically all the interferograms. Also the export for P-rate, and SNAFU, of course, to do the part of spatial unwrapping. These are the supported missions. So you see that there is a bunch of missions already available, and the asterisks are for supporting additional products inside these missions. So for instance, Spotlight mode was not supported on Cosmos SkyMed, I think it is now. And you have more or less all the recent missions are there, which is an important step since there is ESA behind and keeping updating the system. So this is the product model idea that will be, it is introduced and it will be updated in the future. So you can read all the products of all of these missions with specific readers, and then you have a bunch of writers to export the products in specific format depending on what you do later on with your spatial analysis and so on. This is an example of flattened backscatter, sigma 0 backscatter over the Alps. So you can see ascending, descending, you have compensated most of the topography, so it is quite straightforward for interpretation. Then soil moisture tools. To be honest, I haven't used this part in the past, but this is, the Canadians are very proactive on that. So I hope that you have the opportunity also to use soil moisture toolbox for that. Multi-temporal mapping of the INSAR. This is things which have now updated tutorials inside, and you can have a stack of SLC products from Sentinel-1, and you can have all the differential interferograms more or less automatically generated, so you can see how you lose coherence with as you increase the temporal separation from the reference image. Quite important is this multi-reference INSAR analysis, because in the past it was not supported. You could not use, you had only one master reference scene, and with all the secondary ones you could have the pairs, but you could not have the secondary 3 with secondary 8. Now you can control, of course, the time and the baseline parameters to do, you can also visually see that, and you can do this. My only comment to ESA, maybe you will find a problem, is that all these are stored in a single product, which means that if you have a very, 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 very long time series, that would be quite a large file to handle. Still, it has some capabilities when you process specific datasets. And this is an example of multi-temporal analysis, multi-reference analysis with the interferograms and the corresponding coherence map. And you see that these products include inside several interferograms, several coherence, and so on. This is a spotlight co-registration, so it is now available on Snap. I don't know if you see, due to the demulation procedure, you see like you see here the bands, that kind of zonation that you see here. This is well taken care of. So in the past you could not use properly the spotlight mode, but now you can co-register SLC from spotlight mode as well. Ionospheric correction tool. This is quite important for some specific regions. So you have the original interferogram. You have this is not. You cannot correct that with baseline refinement or other procedure, or you remove only the quadratic phase. If you have the capability with split band to extract the ionospheric phase, you can correct the interferogram for this kind of error sources. Yes, so the Pyrite workflow, I will not go to details. But just to tell you that inside now there is an orchestrator script. So all what you need to extract the inputs for Pyrite are already available in terms of script inside the tutorials available online. You have tools to decompose ascending and descending to vertical and horizontal east-west component. And now finishing with what we have right now. So this is the current situation. This is the current operators, and this is what we will have in March 2024. So we will have corrections for ETAD for both SLC and GRDs. We have improved co-registration based on the ETAD, decomposition, spatial temporal analysis catalog stack, and several other classification algorithms. I am also new in that, so I'm looking forward to see all this development. What I would kindly ask from you is if you have some ideas or inputs for us regarding what could be beneficial for development, that would be really great to hear from you. So please come and see me, Marcus, Magda, or other people working on this development, because we can transform, we can add operators in an open source tool that everyone can use. Many thanks.
Thank you, Michael. Any questions?
It will be a polarimetric question? No. Okay. Not yet.
Hi. Thanks for the talk. I wanted to ask, and I realize this might be functionality kind of going backwards for most people who use Snap, but is there any plan to add into Snap, if you know, at any point in the future, image formation capability, so that you could input level 0 raw data and go through image formation to SLC, doing things like autofocus and things like that.
You mean SAR processor?
Yeah, basically, yeah.
I don't know.
Well, I can comment that if there's an open source SAR focusing toolkit, we will gladly support it with Snap, but there's no development plan for that currently.
Okay, so yeah, thank you.
Now the question on polarimetry. No,
yeah.
I'm joking. No, thanks a lot for your presentation. I just want more details on the update for SAOCOM. So which are the plans, especially to tackle the problems of the SAOCOM mission, like the top SAR, which is not really really well done, and also if the tool will be able to make something on the irregular baseline that SAOCOM has. So which are the future plans, or especially for reading the data?
I think to put readers for the different products of SAOCOM, I think that's a priority. Once this is done, I think we need to check carefully which development needs. Also, you can comment.
Yeah, no, we are going to support the SAOCOM tops. I mean, it's a bit more complex than the standard reader. We're going to do it, but still the bursts are not synchronized, so it's not going to be the greatest mode for INSARs. And for the other things, I mean, do you have something specific in mind?
Not really, because we are starting also to work. We are working with polarimetry on SAOCOM, but I mean, this is in our cases because we have direct access to StreetMap, which is very easy in Argentina. So I I will recommend to put the readers, for instance, in order to have access to this huge catalog provided by ASI, because at the moment, I mean, it's useless because there is no formal reader to have that. That is a strong recommendation, I would.
Yeah, thank you, and I think you should also do it in the roundtable discussion at the end of the session. So let's.
Okay.
Yeah.
Thank you very much.
Hi, thank you for your talk. Yeah. Do you have any plan to support burst overlap interferometry for Sentinel-1 processing?
Sorry, can you repeat the question?
Do you have plan to support burst overlap interferometry for Sentinel-1?
We have no plans, but let's talk about it. It should not be too hard.
Thank you.
Okay, excellent. Okay, I propose to move to the next speaker.
Last question, maybe.
Yeah, read the last one.
Hi, thank you for the talk. As we all know, STAMPS was written for MATLAB. And so how does that work in your open access, open user sort of philosophy? And additionally, so as lots of particularly for the applications still available?
You talk about STAMPS, right?
Yes.
But STAMPS processing is not performed within the toolbox. So what you do, you are preparing the reference and all the other secondary image. You put them in a specific format, readable in directories for STAMPS, and then you just execute STAMPS in the MATLAB.
Yeah, and I can make a general comment about STAMPS and the open source. So that's correct, it's not open source, you need MATLAB, but Pyrate is open source and it does SPAS. So that at least is the step to the open direction. I think we need to move on with the session. Okay. Thank you, Michael.
Thanks, Michael. Okay, so I introduce Giuseppe Santolanza from Darius Technology, and we will have a presentation about the data cubes for INSAR project.
Good afternoon. Yeah, thank you. Maybe some of you already heard about SAR2Cube project that ended in 2021, but I will focus more on the interferometric part. but I will have a quick look of all the projects. Okay, back in 2017, we participated to a SEOM project called SyncoMap to retrieve land cover maps through multi-temporal interferometric coherence. We set up different data sets in all over Europe, and we retrieved these land cover maps. But okay, but to do that, we have to store on disk more than 1,000 interferograms, coherent maps, differential phases, and also different kind of multi-look with different windows. So we starting to think that, back in 2017, a way to save space on disk. So what is the basic information we need to use these images with multi-temporal interferometry? So we did a new project called SAR2Cube that the main purpose was to prepare data and store in a platform, in infrastructure, to easy to access, fast, and then post-process with on-the-fly operator. So we did pre-processing based on Snap to register the images over a single reference image. Then we designed the infrastructure that based on Open Data Cube and OpenEO services. And then we developed a set of on-the-fly operator to access these data and process them, analyze them, and we did different kind of application. And most of them are already integrated in OpenEO platform. So here you can find more information about the project and also the repository of the pre-processing and the Jupyter notebook of on-the-fly operator, and also the link to the OpenEO web editor. And
sorry about the technical problems.
No, no, è una indietro. Questa. Non so, lo spingo. Sì. Here, since the project ended in 2021, there is a list of already we participated to already in FRINGE 2021, IGAR's Living Planet, and maybe some of you already heard about this in this presentation. Let's see a little bit what is the basic information we need to store in the data cube, in this SAR-Q2 cube, in this platform. And that is a set of register images to a single reference one. Then the geometrical phase component unwrapped that will be used later with on-the-fly operator for pick up a generic interferogram pair and compute the differential interferogram, and then a set of matrices to transform from slant range to geographic coordinates. So let's see, let's have an overview of the pre-processing based on Snap. Here, as you can see, you can find the link to the GitLab repository. So through an AOI SLC product, we do the registration. And then I will, back in 2021, we did a workaround to retrieve the geometrical phase component, but then we modify the code in Snap. So I will ask Michael maybe to do this update maybe in the next Snap to save the geographical phase component that is the topographical and flat earth component. Say on this. Thank you. And then just, this is done just for the old data set, and then just one time the computation of geographical matrices for the conversion to slant range to geographical coordinates. And here in this link you can find the issue in the Snap forum we open, where it's detailed what we did to achieve this, to store the topographical and flat earth component in Snap. So now we will compute the interferogram and the bars it, and we will get already the bars flat earth component and topographic component unwrapped that can be used for differential interferometric purposes. Once we have the prepared data, we can ingest them in this structure based on Open Data Cube and also Open EO services. Now we can find 6 different data sets that were processed in the framework of the second part of SyncoMap project that will be presented Thursday morning in the thematic mapping session. And you can access them and see what is stored in each data set. Okay. So once it's ingested, all the data set is ingested, we can access them to for different kind of application. We can access them through different kind of client, Python, based on Python, R, or JavaScript. And we can select different features of the data set, analyze them, and get some result. But also we can use the web editor of OpenEO platform to manage all the jobs we want to run and create graphs, execute them, and get the result we want. And use the already on-the-fly operator that are already implemented in OpenEO platform. So here I will go fast. We developed different kind of on-the-fly operator to temporal and spatial subset, compute intensity, amplitude, do some multi-look, boxcar filter, interferometry, pixel selection for PSI. There is not the full chain, but we stopped to the pixel selection. It doesn't go. And the geocoding process also. So I will tell you more about the interferometric part. So we pick up 2 different images, we compute the interferogram. We combine the 2 geometrical components coming from the preprocessing. We remove from the interferogram, we compute the interferogram, and for each interferogram, we just need a complex product and a subtraction, so it can be easily parallelized with this on-the-fly operator. And then we also generated the mean coherence map, select pixel according to a threshold, See, sometimes it goes really well and another.
Yeah, you can do it.
When I do that. Yeah. Yeah, when I do that, thank you. So select pixel and then just without storing all the interferogram dataset, just pick up the pixel we want and save the basic information about the pixel selection over the interferogram dataset. So we just need to save a matrix number of interferograms for number of points. Here you can see the web editor of OpenEO platform, where we can draw the graphs. And here it's a complex graph, as you can see, for generation of one interferogram, but it's easier than the image. And here it's the result. And then here it's just a test we did with an 15 by 15 kilometer AOI. We compute 250 interferograms, differential interferograms. With 4 cores, it took 6 minutes, and with 1 core, just 20 minutes. With interferogram, differential interferogram, coherent maps, mean coherence, and selection of pixels. And here I give you some information on how to access the OpenEO platform and get free access to the dataset and test on your own the on-the-fly operator we developed. And just go through the link, filter by SAR2Q. You will get all the dataset we prepare for the SyncoMap project. And then you should ask these 2 guys, Michele Klaus or Alex Jacob from EURAC, to get the free access to the platform and check on your own. So this is, I think it's a powerful tool for the scientific community that can be used for free, and it's open to everybody. Thank you. And sorry for the inconvenience.
Okay. Any questions for Giuseppe?
Please wait for the microphone.
Thank you very much. It was not clear for me if you applied the atmospheric correction, and if
No,
so,
nothing of that. Just we we co-register the data, and we store in this structure, and then until now we can develop more tools on the fly to do that. So we are open to.
Yeah.
We are still working. So
yeah,
even
because
if
the results in that case, the results may not be so accurate as we wish. No.
This is just the basic interferogram dataset for the next step. Then we can correct the interferograms in a second step.
Okay, and one more. Who are the users of your platform?
Okay, I think OpenEO platform is quite known. I'm not the expert on this platform, but EURAC is really into this OpenEO platform that is, I think it's from Australia. and they are open to develop always new tools, and we are now step by step converting the developing we did in SAR2Cube available in open EO platform.
Okay.
Any other question? Okay, thank you very much, Giuseppe. So we move to the next presenter, José Manuel from REA. I mean, you will present an update of the Snap2 stamp library and software.
Thank you. Thank you, Philip. Welcome, everybody. My name is José Manuel, as already said. I'm going to present the evolution of the Snap2 stamps package, already mentioned a couple of times today. Well, probably, I don't know, let me ask, have you ever heard about this? Yes. You some yes? Okay. So otherwise I need to be a bit more in detail. You see this? How was it, Michele? No. And Mike? Yeah, okay. So let me be from here. Sure?
No, sente. Yeah.
Oh, okay, perfect. That's good. That's good. Maybe, yeah. Let me try. So what is it for? So some of you already know. So it's an open source package. It's based on Python wrapper. The version 1 was still old, so it was 2.7 based on Snap 6. So it was needed something else. And it was done to enable to have an open source DINSA processor to use with Sentinel-1 data when they come. So it was just done for fulfilling actually the need of the user community to do this kind of processing that it was not able to do with open source back by then. Yeah. So why version 2? As I said, it was already 5 years ago, so it needed a fresh update. So now it's based on Python 7, compatible with the Snap 9. And why we were doing that? Because obviously we have a lot of record on papers, research. It's being used also in courses, in trainings, online, webinars. So we thought it would be a good idea to give an update on that. So basically, obviously, during these last 5 years, there were a lot of people with different issues or suggestions or how to do this, or I need a specific different processing, or yeah. So we tried to improve it, to put all together. And it was obviously early this year, just before the deadline of the abstract, I got contacted by Jonas, one of the authors, that he was he modified the original package to have it compatible to use with TerraSAX. So we thought it would be nice also to include and expand the list of supported sensors also with a workflow for TerraSAX stream map. And at the end, we wanted to make also things easier because the user community is quite large. Some of them are more experts, some of the ones don't. So we tried to make also easy the installation and the usage of this tool. So some of the features of the new release that happens actually this weekend, I just managed to publish it during the weekend. So as I said, it's based on Python 3.11, Snap 9, and then we have for single burst interferometry, it was before releasing a question regarding something like that. We support external DMs, or we expanded the definition of the AOI. It's not a bounded box or well-known text, also supports shapefile, KMZs, and GeoJSONs. We also provide some plotting, because before they were not providing any script to do the plot, so the user should look into it every time. And some other functionality for example, Sentinel-1 auto-download based on Alaska satellite facility. Why only based on Alaska? Because now all the Copernicus Sentinel data is evolving, so providing something that will expire tomorrow would make no sense. So we will work on that maybe in the future. So this was the workflow that was doing the version 1. So you see, maybe you still remember that the master splitting was still based in opening the Snap GUI, selecting the OI. So now in the version 2, this is automatic as well. So also based in the gathering the feedback of some of the users to how to do this and how to do that. So we were expanding the capabilities, the functionalities, and as well the sensor supported. So you see now the right-hand side, you have all it's similar workflow because it was based in the same package. But obviously the TerraSAR data is provided in different format, different things. So there were some adjustments that Jonas did himself, and we incorporated in the version 2. Yeah, it's quite simple. So as I said, in the original version 1, the minimum unit for interferometry was compatible with 2 bursts. So that was because we thought it was basically most of the cases will fit in there, but maybe people want really small area or wider area, right? So this version includes supports also the one single burst interferometry with the proper graphs, but also, yeah, with minimize actually the time if you do only that. But it also is compatible with merging subswot with different amount of bursts, single burst with multiple and so on and so forth. 3, the entire subswot, but obviously you need the resources for supporting this processing. Yeah, and the merging is done, well, the interferom is done still subswot by subswot, and then we have the merging before the stamps export. So here's a bit how it looked like, the new extended support for AOI definitions. So now we support all these kind of formats, which are many more, but we thought that these ones are already quite large list for the common ones used. And yeah, how it looks like now in this project.conf configuration file for which the package is based to get all the parameters. So you can, what is it here? No? Okay. So you have the mode, and depending on the mode, then the software reads either the definition of the coordinates or either the well-known text or the path where the AOI file will be found. So then, as well, for the plotting of the press data, we came into it because at the end it's always recommended to spend some time to see how the interference look like before doing through the entire PSI processing, because you don't know whether the resources were not enough and it was not, the entire interference was saved on this properly, there was no space or the resources or something happened. So it's better always to have a look at it in the interference before proceeding to the PSI, for which you will have another different amount of errors to solve, or APS, or whatever else to take care of. So, oh, a bit through, right? Yeah. So this was it. Okay, yeah. Here I just put some slides just to show you all the different parameters that they are now the list expanded a bit. But as I said, there are some of them that are based on the optimization of the disk and so on, the processing options. So you want to override, so you launch the same processing over the same project, but you have more images. If you don't want to overwrite, it will only process the new ones. Before it was processing the entire directory that was there, right? So now this will be avoided. You can have a smart disk, what I call it, that basically will remove or optimize all the different elements that they were repeated. It was the DM elevation band for each of the exported pairs, or you have also the master SLC for each of the exported pairs, but this one is always the same information. So in this case, we remove it from all the pairs that they are not only keeping only one, and basically creating soft links of the other ones. So the software thinks that their products are there entirely, so it's able to export it without any problems. Yeah, and then here as well for the auto, for the master or for the project itself, you can define which is the sensor, which is the polarization. Now we need the master folder, not the master file, because before it was only based on a single subswot, so it was pointing to the subswot that it was subsetted. Now, as your area of interest may have 1, 2, or 3 subswots, we just need the path to the folder where the master is saved. But actually, this one is the zip master image. It can be multiple master, we will assemble, But yeah, for the rest, it's a bit modified with respect to the version 1. Then we have also the auto master selection. So here you can select whether you want to have the master the first image or the last image, or if you select manual, you may put there the number of the master sample you want to get. So the image number 10 or the image number 15. And as well, the last one, maybe it's a bit confusing, is just for the path to the external DM if you want to use any. Again, showing the AOI definition, but it's part of the project configuration file. And then in the right, also the Sentinel-1 auto-download that I incorporated here that is based in the ISF search package from ISF. So we based on that, but actually we kept the same parameters, but you can come here and just define what you want, and it will do the query and the downloading, but you need to have an active registered user on ISF and put here the user, the user and password in the project configuration file. Okay, just the last thing, you need always to put where the snap installation folder, and now also where the home directory, the hidden one, which are the color palettes and so on. So we produce the interferons with colors and so on. So this is it. Okay. So now the installation, it is only these 4 steps. If you are using Ubuntu, for example, you have to install the dependencies of Snap, which are the libraries of FFTW and libgfortran to create the interferons properly. These operators need these 2 packages. Then you can download the GitHub of the package and create a conda environment, which actually this one is not only taking care of all the packages that are needed, but also includes a conda package I created myself of Sentinel-1 Toolbox version 9. So you don't need to download the Snap anymore, the version 9, with the update of 9.02. So you can just really conda install, conda create this environment and downloads the Sentinel-1 will be installed automatically as a conda package. So this, so people will not be confusing anymore if I'm using Snap to stamps. I have a Snap 8 or a Snap 7, or I will have a Snap 10. So we will first, it will not be incompatible anymore. You will be able to have different versions, your own one and the Snap to stamps Snap installation. And then it will probably easy things, so you have an error, it will not be based because it's incompatible. So this tool was tested with 3 different sites. 2 of them were with Sentinel-1 data, and 1 was with TerraSAR-X data. Well, several gravity dams. So maybe Jonas may have more information if they're split in different data sets or one single one, but I think it was one single track. So, so it was tested end to end. So I did a snap to stamps approach and then also the PSI to see whether the results were something expected, because when using Snap 5, we found some issues that we reported to the developers. So that's why the first version that was compatible was Snap 6. So we did an end-to-end processing to verify that things were working, like pointer, thank you. So here, for example, one of the areas, the Abu Dhabi, which this morning I saw there was plenty of RFIs, indeed. Abu Dhabi and Dubai area is plenty of RFIs. So we use 25 free RFI data for, I think it was 2018-19, I think. And this is only 1 year, so don't try to take out any explanation of analysis what the deforming could be, because it's only 1 year data. And then for the, thank you, for the TerraSAR, well, we have a sample of the data, but still the PSI results, click again please, are not that yet because are going into the publication of the author itself. So it's based on the PSD, so I hope that everything will go in the right direction on that. Please go next, yeah. So basically, this is it. So there is not too much on that, but yeah, there's a nice update in which I believe it will be used as well as the version 1. Thank you very much.
Yes, thank you, Jose Manuel. I think we have plenty of time for questions.
Thank you very much for the presentation. My first question is if you are planning to adapt the software for SBAS. It will be great.
Yeah, it's only time-related things. If I may have time for that, yes. I have some requests in the queue for testing it, and I see today that Michael showed the multi-master selection working, so probably will be one of the candidates for the next release, yes.
Great. And also, the second question, in the last version, when you did the split step, the whole subswat was stored?
For the secondary images, yes.
Yeah, so
this
now,
still is the same here.
Yeah.
It is a bit large, but we ensure if you have any misalignment on the metadata of the products, that at the end the final product covers the area you wanted. Because we saw even with the testing of the phase and the passing of the years, with so many cases in which we try to use the same smart splitting for single bars or 2 bars, and in some cases you may find data that is not properly subsetted.
Okay.
So maybe metadata product or maybe something else related. So I prefer to keep the entire subswat split, so at the end the data gives you what you want. It's a bit more of hard disk resources and processing. Well, processing not too much, but these resources you need to have, yes.
Yeah, you can always change it in the graph file, no?
Yeah, sure. You can also change it. I prefer not to include it because otherwise could lead to these other errors. But I mean, it's just an update on the XML, yes.
Thank you very much.
Welcome.
Another question? Thank you very much, Mr. Manuel.
Okay. Yes. Just I would like to invite you everybody to test it, as now we have also the stream map supported sensors. Take in mind that also not only TerraSAR, Cosmo, and all the other stream map data should follow the same procedure. So maybe we could. I mean, it's an open source project. Everybody is welcome to contribute. The authors and contributor list is not closed, so please don't be shy and call us. Thank you.
Thank you very much. Okay, so no, I think it's Martin, I guess. Oh. Sorry. Yeah, so the next speaker will be Martin Jussi from CGI, and you will your talk is about high-speed GPU INSA processing.
Good day, all of you. Good to see you. Let's see if this one works now. Yeah. I'm Martin from CGI Estonia. I'll tell you a bit about GPUs and SAR processing with GPUs. You will hear about a project background, the functionality of the software we've developed, some processing tools, examples, and performance, and some latest, newest developments and opportunities enabled. So I'll start with the GPU technology introduction. So you may have heard of the GPUs, but I'm not sure if all of you are really familiar with them. GPUs are a graphical processing unit, so traditionally the graphics cards of your computer, which in the olden times used to be mainly used for video rendering or gaming. So anything really video related, like computer games or videos, we're using the GPUs. But in the contemporary world, they have been evolving a lot and getting much more of a generic use, especially really in the latest developments of the AI models have been kind of pushing the GPU development. So now they're used for AI model training. Also for cryptocurrency mining, that's a common use case, but the technology itself has become rather generic, so you could do various computational tasks that you could parallelize on the GPUs. So the idea of the GPUs, or really the benefit of the GPUs, is that you could do really massive parallelization of your code if your algorithm as such is parallelizable. What's that word? Yeah. So on a single GPU, you have hundreds or thousands of cores instead of a few, like 4 to 8 that a normal CPU would have. So the effect you get from GPUs is that if you parallelize your work, you get a very, very high acceleration. So there are some common languages or tools that are being used. So the most well-known technology is the NVIDIA CUDA, which is supported on the NVIDIA GPUs, which you could find on most processing clusters nowadays. And there's also the OpenCL technology, which is open source, but I think it's a bit deprecating by now. So the performance trend is such, you may not see the labels on these figures too well, but what really matters is the essence of these figures and the graphs themselves. So the GPU performance has been advancing massively in the recent years. So the performance improvement over years is not really linear, it's exponential. So, which is not the case with the CPU technology. So CPUs, of course, are getting better as well, but there's really been a massive massive burst in the advancements of GPU technology in the recent years. And why it's so important is because of this. So you can kind of see the similar trends in the Earth observation data growth, and year over year you will have to cope with much more data. You will have applications that leverage different data sources, so somehow you would have to be able to process all this data that you're generating. So to tackle this problem, we have created a little software tool that we have called the ALUS toolbox. The ALUS, it's just a name, but you could think of it as maybe arithmetic logic units or something. So it's an open source tool set leveraging GPU technology to accelerate EO data processing. Today, we have also mostly been focusing on SAR, and our today's presentation is also focusing on SAR, because this is a SAR conference. But the toolbox is open source. You can go ahead, you can test it, you can give us feedback and ideas for improvements. Here's a link to the repository. On a later slide, I'll also have a QR code. So again, open source project, and it's mainly developed throughout several ESA projects. So we've been very closely cooperating with SFRINGE on this one, and it's either been under development or used for adding value in 5 different ESA activities nowadays. So from the very early start of the development of this toolbox, we took on kind of like a user-oriented approach. So we started consulting the SAR community to give us input on, essentially which algorithms are you using to do your work, and where are the processing bottlenecks? Which ones are the slowest ones you would like to get accelerated? And we based on our developments on that. So there are some names mentioned here. At least one of them is in this room. So there's been a quite diverse expert user community that we've been engaging, and we've got input from them. But they all seem to face pretty similar problems. So based on that input, we decided to develop a number of processing algorithms utilizing GPUs. We call these routines. And we've also been highly engaging with the Snap user community, and also we've actually been used, especially in the early days, we used the Snap toolbox as a kind of a reference implementation. So basically even like a kind of a ground reference data or a validation data for us. So we basically compared our results to the results from Snap. And moreover, we asked these expert users the questions like, okay, you do coherence, but show us the exact Snap functions that you're using and tell us which parameters you're changing, which ones you're not changing, which ones could be hard-coded, etc. So that gave us some ideas for the routines we want to develop. So we have a coherence estimation routine, a calibration routine, a more specific and a bit fancier timeline generation for coherence, and a generic resampling routine, which is not only applicable for SAR, but also for optical. And we have some SAR focusing things, which I'll tell you a bit more afterwards. So the coherence ones, the figure on the left is the coherence estimation routine, which is basically generating a coherence pair using GPU acceleration. And this is a very, I mean, you could recognize this if you're a common Snap user. So these boxes here are simply, each of them is a separate function in Snap as well. So we've been kind of trying to get the exact same results with our GPU-based approach. So these are the functions that we have implemented. And on the right is the coherence time series generation routine, which is essentially the same routine, but it has some sophisticated data handling mechanisms in order to really facilitate the usage of the generation of long time series. So you could have just 2 inputs or 10 inputs, even 20, 100. You could do that processing automatically. We also did accuracy assessment. We always do accuracy assessments against some, let's say, reference software implementation. So in this case, it was the Snap implementation. I think the version was something like 8. And the figure here depicts the kind of relative error in each pixel, but that's in, you could see that the relative error is in the order of around 10 to 100 pixels per million. So it's really small differences, quite insignificant. So the accuracy of our results compared to Snap is very, very high. For the calibration routine, this is a simpler one. Is essentially for generating calibrated geocoded Sentinel-1 products, and quite straightforward. Nothing too fancy, but also very fast. And this we've got even closer to the Snap implementation. So very few differences. Highly accurate. So on top of the algorithms, I'll tell you about the focusing ones afterwards. We offer some general functionality. So if you've all of the functions, all the routines are GPU enabled, GPU accelerated, and they work on NVIDIA GPUs because we use the CUDA technology. And based on which GPU you have, we make kind of smart use of it. So if you have those very sophisticated GPUs like the NVIDIA V100 and I think the H100 also, they provide capabilities of kind of partitioning the GPUs. So if you have sufficient GPU memory, you could even run multiple instances of the ALOS toolbox on your one GPU. So if you want to process like 100 images, you wouldn't need 100 GPUs to parallelize that. You could have maybe 10 or 20 GPUs in your cluster. You could still do it because multiple instances of the software could leverage a single GPU, so partitions of one GPU. Also, the inputs to the software, so the scenes, the inputs are supported at multiple levels, so you could provide the full Sentinel-1 scene, only one subswath, or you could also do the processing on burst level. But you could also, it also supports a user-defined, so an AOI-based area of interest-based input in the shapefile format or just well-known text. And you could run it globally because the Copernicus DEM 30 is also supported. So our approach has been on so focusing on pure processing, getting the processing routines fast, very fast and reliable. So the software simply has a command line interface, which allows it to be integrated into an existing processing environment. All you need is a Linux environment, GPUs in your cluster, and the data made available. Any kind of analysis you would need to do in some other tool, which could be the Snap Toolbox or QGIS or whatever else. And we're also taking the approach that the auxiliary files would have to be provided in the processing environment. Of course, you could have simple means to download them, but we've been trying to have as few external dependencies as possible. Yes, and there are some, in our repository, there are some Docker images available that you could use. There's one also with the Jupyter Notebook as a front end. So if you use the Jupyter Notebooks and you don't like the command line interface that much, you could also try the software out with that. And here is an example how the input to the coherence routine looks like. So you just specify your reference scene, your secondary scene, the output directory for your results, and also the region of interest is a polygon, and the DEM files. Okay, also a bit about SAR focusing. So last year we had an ESA TDE activity called BULP, so the bulk processing via parallel computing. And within that project, together with our colleagues from SARMAP, we developed a prototype processor for ALOS pulsar zero Doppler focusing. And we achieved very high, very fast results. So the output was nearly interactive, took around less than 2 seconds to focus a full pulsar image. So this has huge potential to develop into a serious, real on-the-fly processor. It supports several modes. And you can see the output figures here and also the processing chain as such. I have a particular slide about the processing performance of this SAR focusing. So the total runtime of the focuser was around 1.7 seconds for one pulsar level 0 product, which is around 203 megapixels, so a quite large image. And the calculations on the GPU took around, what you can see there, like something like 0.3, 0.4 seconds. So a key message here is that we know that the processing on the GPU can be very fast, but it could also be the transfer transfer of the data to the GPUs from the CPUs could also be a bottleneck. In this case, we also did that very, very fast. So the end-to-end processing of one scene took 1.7 seconds. So for this case, I mean, if you need to really have a large reprocessing campaign or such, I mean, this kind of software really enables that. And now for some recent developments. So based on the success of this previous activity, we decided
you have
to
2
continue.
minutes.
To continue with SAR focusing. So as part of the ESA QA for EO service, we are now developing the NVSAT ASAR and ERS SAR level 0 processors. And we have already some preliminary results. I mean, here's some graphical example, but the message is that the focusing can be done. It's on the order of magnitude. The speed is on the order of magnitude of the previous slide. So we could do that in less than 2 seconds. Process a full level 0 scene. So in the future, we could really have interactive processors that help access the users access heritage data. So very fast on-the-fly processing could be done, and also any reprocessing campaigns could become much faster. I mean, if you need to process 1 million scenes, if it takes less than a second to process one scene, that becomes reasonable. And again, I mean, this is also going to be open source. So here we have the open source SAR focusing tool that Marcus is willing to support in Snap. So just have to wait until next year. So the ALOS tools have been also put into quite meaningful use. So as part of the C-Scale Horizon 2020 activity, Guy Dolimon from the European Commission's JRC used our software to produce a year-long series of analysis-ready data, analysis-ready coherent state images over Ukraine to monitor agricultural activity during the Ukraine war. And he was using the CreoDias environment for that, and to generate the coherence pair, it took around 11 seconds per subswath on the GPUs, which is again very, very, very fast. And we are really proud of this use case because this shows that the software really can be put into meaningful and good use. Quick words about the potential opportunity. So this is just a concept that we've come up with. So if you can generate any products in milliseconds, then why would you store intermediate products at all? So we could do on-the-fly processing directly from raw data into whichever level needed, to level 1, level 2, level 3, and deliver it directly to the users. So you would save on storage costs, you would get very fast time to products, less overhead in processing, and you wouldn't need any reprocessing campaigns at all because you would generate the products always from level 0. We think that the GPU technology can make this really possible. So thank you very much for your attention, and I'm here until Wednesday, so any discussions, questions, I'm open to discuss.
Thank you very much, Martin. Any question?
Apologies if I missed this, but I'm assuming you're using like the range Doppler algorithm to focus this, like a frequency domain algorithm? Okay, cool. And what kind of GPUs were you using? The performance is really impressive, so just wondering.
We've been testing with different ones, mainly the NVIDIA ones, A100s, B100s, but also over time, not that advanced ones. So different grades, usually the ones you get in the common processing environments. Yeah, I can't remember many models from the top of my head. Yeah.
Okay, yeah, because running this on like a laptop with a smaller GPU, is that also possible?
It's
and
possible,
do you get similar processing times?
Yeah, you would be on the same order of magnitude, but probably not that extremely fast as with a really server-grade GPU.
Awesome, thank you.
One of the more computationally intensive parts of some processing is pixel offset tracking, the cross correlations. Are you including that in your GPU code?
No, we haven't worked on that, no.
There's another, it's used the microphone.
Yeah, that could be parallelized massively, no? What do you think?
That's a good idea for the future, yeah.
And perhaps a comment? You should perhaps advertise also that the consumption of a GPU is less than the CPU. So...
You were saying, sorry?
The consumption of the GPU is generally less than the CPU.
Energy consumption,
yeah,
you mean?
The energy consumption,
So, per se, like what our experience is, I haven't done a very deep analysis, but if I remember correctly, the power consumption, that was in some article that was published. So the average power consumption of a GPU is around double of a similar CPU. However, if you could do your processing 10 times or 100 times faster on the GPU, the total power you'd be consuming is much less. Yeah. So yeah, definitely also from a power saving perspective, if you are doing very large processing campaigns, this becomes reasonable. Yeah.
Okay, so then it's time to move to the last speaker of the session, Pius Agram from Descartes Lab, and he's going to talk about GIS-based workflows for SAR/INSAR science data systems.
Hopefully I won't go too much over time here. So we are a data engineering company, which means we specialize in handling large volumes of data and high-performance computing. Today I'm going to talk about SAR/INSAR workflows that we've developed, and when I say GIS, I actually mean you're doing all the processing within a GIS framework. I'm not doing it outside with the tool and then bringing it into a GIS software visualization. I'll also present some results from our applied science team who use the product that I'm going to talk about extensively. I'll describe our Sentinel-1 workflows in a GIS-based framework. I'm going to talk about how standard SAR/INSAR applications are easily done within GIS. You don't need special software tools. Then I'm going to talk a little bit about multi-sensor, multimodal analytics, which is mixing Sentinel-1 with other sensors. And talk also about upcoming global SAR missions like NISAR, ROSEL. Having implemented global scale Sentinel-1 processing the traditional way that all the previous speakers spoke about, and having implemented it this way, I believe we really have to consider using the GIS approach for things to be cost efficient, energy efficient, and scalable going forward. There's also a lot of open small sat data coming out. I'm going to comment a little bit on what we are doing to prepare for processing that type of data within GIS frameworks as well. And in the end, I'm going to talk a little bit about what we can learn from other Earth observation data sets. We sort of tend to live in our own isolated world and not keep track of developments from other types of sensors. There's a lot to learn, and I think this geocoded SLC concept is something we should pursue more actively. This is a slide from FRINGE 2021, where we presented our global scale work on Sentinel-1. We routinely process 3 products out of Sentinel-1. SAR backscatter from all we transmit data, which is dual pole, single pole. This is on a 10-meter UTM grid. The UTM grid is compatible with Sentinel-2 from get-go, so you can overlay them on top of each other for mix and matching them. We do all interferograms less than temporal baseline of 24 days. And all these products are done on a burst-by-burst basis. We also do a product called RTC Factor, which we demoed in 2021. I'm going to come back to it a little later. We're going to talk about how radiometric terrain correction, you don't have to do it every image. It's really a waste of resource to recompute it for every image, incoming image. We use geocoded SLC bursts, which you heard before today. It's great. Opera is going to do that over North America. But this pipeline that I'm talking about has been operational for 2.5 years. Close it. Around the mic, yeah. So this pipeline has been running for 2.5 years. It's hands-off, it's automated, and we process all retransmit data globally. With the upcoming global missions, we expect, at least on our side, to have a similar suite of products. Whether the missions themselves generate it or we generate it is a question for us going forward. Just a brief overview on geocoded bursts. You all know Sentinel-1 SLCs are distributed in safe zip files with TIFF files, and each TIFF file has a certain number of bursts. For us, the processing unit is one burst. We don't need the entire zip file. We've built data access mechanisms where we can pull the one specific burst we want over the network in 5 or 6 seconds. Could be anywhere in the zip file. We've mapped all the bursts for Sentinel-1 already. And the processing, because we don't need the whole zip file, we don't need large disks. We could do the entire processing in the 3 GB and 1 CPU. So it's like super cheap for us to do global scale processing with this. Eventually, what we end up with, starting with the burst in traditional slant range coordinates, is this geocoded burst on a UTM grid that's 10 meter northing and 2.5 meter easting. We chose this first for compatibility with Sentinel-2, but also this has nice oversampling factors over the actual data resolution. So we're not introducing any artifacts by geocoding early in the processing pipeline. Once you have the geocoded bursts, then backscatter is absolute value of the complex number. Interferogram is cross multiplication of complex numbers. No, you can throw whatever filter you want. You don't like boxcar, you like Gaussian, you like some weird shaped filter, you pick, you can do whatever computation you want on the file. And all of these can be done within your standard QGIS, whatever GIS software you want. You don't need any special tools to do this. This is very similar to the geocoded SLCs that Howard Zepker proposed in 2017, but he proposed focusing the data directly onto a geocoded grid. If you're able to do that with all calibration accounted for, great. In this pipeline, we start with the calibrated SLCs and do the geocoding. Like I said, radiometric terrain correction. I refer to you to the paper that came out earlier this year. Radiometric terrain correction is essentially the process by which you account for difference in imaging geometry. That's essentially what you do in INSAR as well. They're the same operations. One is correcting amplitude and one is correcting phase. So they all are related to baselines. And we know Sentinel-1 has this narrow baseline tube. So it's same as INSAR processing. Pick a reference image, you compute the correction. And for Sentinel-1 specifically, since the baselines are small, that correction is more than sufficient for radiometric terrain correction of every incoming image, which means you have a stack of 400 images like somebody showed over Europe. You only need to compute this once. You don't need to expend resources 400 times to do this. You just compute this once, every incoming image, do a cheaper geocoding operation, and then add this correction factor on. You don't even have to add it on the fly. This is what people who work with Landsat and Sentinel-2 do. They do red, near infrared, and NDVI all the time. It's the same plumbing, same framework. It's band map. Since all our products are on the same 10-meter grid, nothing fancy. Simple math operations between these images are sufficient to do radiometric terrain correction. The other thing this enables, which was something that used to annoy me a lot personally, maybe not other people, is that the RTC folks have their set of tools, the INSAR folks have their set of tools. They don't talk to each other. They don't produce products on the same grid. There's no consistency between them. They want to do their own grand processing job. They want to do their own, but this sort of framework allows you to do all of that consistently and have good statistical properties. Having implemented all this in Sentinel-1, this is my personal recommendation that we don't really need GRD products. Using GRDs is way more expensive than SLCs. If you have the right data access mechanism to access individual bursts, you will end up reducing your processing costs by an order of magnitude, because you'll be using smaller computers, a lot less memory, a lot less disk space to produce the same set of outputs. So if GRD products can be eliminated and that budget can be used for something more useful, that would be awesome. That would be my personal recommendation. In the process of, if you go see the paper, we also noticed that we built unit tests, and SNAP performance in radiometric terrain correction is not very good yet. We will definitely be revisiting this as newer versions of SNAP come out, and we've described elaborate experiments on how you can actually test this out. We've also shown in the paper that this is not, this framework can go as far as like ALOS-1 baselines, which is 6 kilometers. So basically, any modern INSAR compatible mission, you get radiometric terrain correction for free if you make the right equation changes in a couple of places. So the common INSAR applications that I've encountered from users, I've seen on Snap user form, is basically they want a radar backscatter, they want INSAR coherence, and they want INSAR phase. And for us, since we process these products globally, accessing these and making a GIF out of it is like 3 lines of Python, just the way we build GIFs out of Landsat or Sentinel-2. These are sort of foundational products on which we build our analytics pipelines. Some of the examples of these are, we have something called quick look velocity or time series. How many of us have wasted times, like I want to do an elaborate stack processing and then find out this area is not really suitable for INSAR analysis. For us, we can arrive at this conclusion in like 5 minutes. We'll be able to run a quick look notebook over, say, a 5 kilometer by 5 kilometer, and then decide whether, oh, this is a hotspot, whether it's worth investing all this processing time into generating this computationally intensive stack. We had a summer intern this summer, Rebecca from University of Texas Austin, who built it, who basically took our quick look notebooks and made a simple Python interface that you run in a notebook. You just give it a lat-long, a kilometer size, and start date and end date, and say whether you want velocity or time series, and anywhere in the world you'll have analysis spit out in 10, 15 minutes, because we have the global interferograms less than 24 days globally. We also do full resolution infrastructure monitoring. Okay. So we also do full resolution infrastructure monitoring with Sentinel-1. In this case, the reason I'm pointing this out is for full scale resolution, you need the data to be complex valued. So in the previous case, we were deriving the quick look stuff from real valued coherence, real valued phase. Here, it's complex valued data, but the data we access the same way. Like you give a box, you give a UTM limit, and it pulls out pixels, and you have your complex image, you cross multiply and do your time series with it. We call this geocoded SLC. GSLC is the abbreviation we use. We've also done this with other sensor data, like TerraSAR-X and Cosmos, SkyMed, over limited AOIs where we could get some samples to play with. But this is this powers our infrastructure monitoring anywhere. Since we operate on bursts, if you come to us and say, I want to monitor all volcanoes, first of all, we already watch it with our global product. And second, if you want the all bursts following monitoring all volcanoes, it's like 400 bursts, 500 bursts. It's really straightforward to scale up the processing. Or you have 200 mines you want monitored. It's really easy for us to just scale up the processing at that level. The other thing I want to talk about, especially since I was talking about GIS, is the multimodal analytics. I'm using one example here of deforestation, but the same applies to, say, agriculture, generic change detection, surface water. Deformation analysis is pretty much the only application where Sentinel-1 data is used by itself. In every other application that done by our applied science team or our customers, they're always mixing data from multiple sources. Sentinel-1 is not the only source of data they're going to use to make decisions. So if you're going to build your data system focused only on SAR, you're going to hit a roadblock at some point of time. In this case, we're using Sentinel-2, NDVI, Sentinel-1 backscatter, and Sentinel-1 coherence. And you see all of them have this nice signal around the deforestation event. This is elaborate analysis done by our applied science team for a couple of validation sites, where they did analysis purely with optical data, purely with SAR data, and then mixing SAR and optical. We're doing, this is the simplest example I could find. Think also that Landsat is used extensively in this. So there's actually more sensors typically. Clearly, SAR coherence plus backscatter plus optical is what makes the most number of reliable detections, not just optical, not just SAR. And just extrapolate this, and this observation is consistent for agriculture change detection applications at our end. So based on what I've described or what we've built for Sentinel-1, how are we preparing for the upcoming missions? NISAR, ALOS 4, Roselle, they're all designed to, I hope I got the ALOS number right. They're all designed for persistent INSAR analysis. Backscatter is okay, it's easy. It's probably the easiest application you can do with SAR, but it's not the only application. Coherent change detection has proven to be really important based on feedback from our applied science team. Phase measurement for deformation is another useful component. Though L-band gets noisy, but still, it's going to be a useful component. From our point of view, what we expect from these missions is, at a minimum, access to calibrated high-quality SLCs. I would say GRDs are not worth it. That is our feedback. And when I say quality, it's not just imagery. It's the quality of the metadata. It's like, how good are the orbits? How good are the timing corrections? How good can I geolocate it out of the box readily? That's what I'm talking about when I say quality. SLCs support both backscatter and interferometric applications. In general, having worked with a lot of SAR data and Sentinel-1, Sentinel-1 has raised the bar on what is the minimum acceptable level. Every new global mission that comes out, I think, will be compared against Sentinel-1 for ease of automation. So if you are operating in a burst-based mode, I strongly believe you should support data organization and direct access to these bursts. That should be the minimum requirement going forward. If you are not a burst-based system, you should use a clearly defined track frame system to enable automation. The volumes of data that we're talking about from these missions are so huge that a human operator cannot keep up. So you really have to think about how you're going to automate all this processing. We are really excited on the analytics side for the coherence and backscatter at C-band and L-band being available at the same time in about a year from now. So on the analytics side, we are preparing for that as well. There's also a lot of sub-meter resolution SAR data coming out. Capella, Umbra, ISI. Our experience working with this is for automation, you really need improved DEMs at a global scale before you can automate processing these. Right now, you can sort of automate some processing. You can go get LiDAR DEMs over select areas. But if someone sends you a high-res image to you, you actually have to expend quite a lot of effort getting a reliable high-res DEM. So I think the first step before operationalizing, automating this sub-meter SAR space is we need 3-meter or 5-meter DEMs globally. Reliable, high-quality DEMs globally. Till then, there's always going to be a human in the loop. There'll be human. You can only automate it to a limited extent. The other challenge is these small satellites so far, we've had to deal with a fairly large diversity in imaging geometries and modes. It's not like Sentinel-1 with a narrow orbital tube. You're often asking yourself, is what I'm seeing real? Is it change that happened on the ground, or is it change due to the imaging geometry just because you happen to be looking at the ground from a different perspective? So far, at least currently today, often requires manual intervention in the interpretation stage. So hopefully, if possible, if their imaging geometries and modes stabilize, that will help automation in the analytics side. We've also sort of automated some standard applications. Here's a standard motion detection moving target indication analysis from a single SLC. Once you geocode an SLC, you can't go do subaperture analysis. So what we do is you create the subapertures and just save it as 10 bands of an image. It's like Landsat, but each band of the image is a different subaperture, and then you can automate it and color it. And there are some applications you could do fairly out of the box, but when you have more than one image involved, you'll have to actually have a human right now for interpretation. And working with our applied science team and talking to our customers, there's a lot that we in the SAR world can learn from the rest of the Earth observation space. We are a big part of the Earth observation solution. Everyone believes that, but everyone's also clear that we are not the only solution. Interoperability with the other Earth observation data sets is very important. I find it easier to communicate SAR data characteristics with our applied scientists by bringing it early into the GIS framework. I think it'll lead to broader adoption. part of the reason why we started with Sentinel-1 grids that are compatible with Sentinel-2 from the get-go. The other thing we tend to do a lot is like we overemphasize the need for specialized tools for SAR. You don't really need to overemphasize it. For all practical purposes, SAR processing, the SLC you get is in its custom projection system, and you use a very specialized custom interpolator. So you could say it's a GDAL1. It's not really much more fancier than that. So we need to start training people to think about SAR data that way, rather than we throw them into the deep end with like, here's a software you need to do, here's the input files, here's the output files, without really wanting to delve into the internals of the software. The Earth observation community is very comfortable with map projections. There are plenty of sensors out there that use weird map projections. SMAP, GOES, MODIS. They have no problem with that. And it's part of the communication. You communicate to them that what you have is a weird map projection, they get it. I think that's another sort of eases the barrier to entry. And one thing we could really do, which I hear again and again, is coalesce around a usable level 2 product. For most Earth observation data sets, number of level 2, level 3 products is significantly greater than level 1 products. We don't have a standardized level 2 product in the SAR world. A large majority of the users just do the same standard processing themselves again and again. So hence the work from JPL folks on geocoded SLCs, I think is a good start, and I think we as a community should start thinking about coalescing around a geocoded SLC as a proper level 2 product. Supports backscatter analysis. User can go do multi-look themselves as much as they want. Supports INSAR, again, as much multi-look and filtering as you want. Keeps manipulation operations simple, very GIS friendly. We have also shown that the standard RTC correction is nothing but band math in GIS frameworks. So that is not a hindrance. You get to preserve resolution in a GSLC product. Also for a lot of the sensors, like the small-sat sensors, where each image has its own resolution, you get this intermediate level where you get to standardize the product. You could have whatever resolution at the original L1 SLC, but you could say my GSLC is always going to be 1 meter. Makes life easier for the end users to work with. And the other big takeaway for us, at least, is the scalability and simplicity of the maintenance of these workflows. The processing costs go down by an order of magnitude. If ALOS 2 had put out burst-based products, I bet our processing costs for doing ALOS 2 would have been 2 orders of magnitude lower. So there's a lot to be thought about in terms of how data is distributed and how level 2 products can be built from level 1 SLCs, which people find hard to navigate. The one important con is this makes requirements on the data quality from the providers more stringent. The quality of the metadata has to be high, quality of the imagery has to be high for all these workflows to work this easily within GIS frameworks. That's all I have. I've included reference to our previous talks in the last slide as well.
Okay, so we have time for a couple of questions.
Thank you very much for your presentation. It's super exciting. I have just a technical question, and because I like very much this idea of geocode SLC, but when you geocode, what you really obtain is and you process to obtain coherence with the geocode, you have no longer a constant number of looks when you process.
That is correct.
I mean, I know that this is a technicality, but have you figured out a way to try to solve that issue? To assure that when, I don't know, you make a box plot, boxcar of 5 by 5, you obtain 25 equivalent constant number of looks, which is for some statistical analysis, for instance, for classification, it's necessary, and you eliminate this additional variable on the data.
I completely understand. I think our solution to the problem was we switched the product under the hood, and the customer didn't notice it.
Repeat again, sorry.
Our answer to this was we did a test where we switched the product under the hood. One process traditionally and one process this. And the customer really didn't notice it. So I think this claim that this is a problem, I understand it's a problem mathematically.
Yeah.
I think we need to do that comparison regressively to show that it is a problem.
When you filter many looks,
Yeah, exactly.
it's no longer a problem.
I
accept.
From my experience, people really didn't worry about it when they looked at the new problem.
Yeah, but when you want to analyze or to make some accurate statistical analysis for PDF description, and if you want such amount of data to I don't know, to make kind of a big data analysis of statistics, I mean, at least I think this...
I completely agree with you. This is what I would call a standard trade-off question.
Yeah.
How much error am I incurring more? And I suspect that number is going to be smaller than to worry about.
Okay, thank you very much.
It's a trade-off study that needs to be done.
Thank you very much.
Thank you for your talk. It's really great. I just want to ask that you plan to generate 5 to 10 meters global DM, or what kind of satellite data you want to use?
Oh, no, we are not planning to generate the DEM. I'm saying that is a prerequisite that the whole community should think about. Like, we won't get to operationalizing use of sub-meter data till we actually have a 5-meter global DEM to get there. I don't know how we are going to get there, but if someone claims they're going to do global Umbra processing or Capella processing, I'm going to be very skeptical. Because I think to get there, the first step is to get to a reliable 5-meter global DEM first.
Oh, thank you very much.
Excellent presentation. What do you think is preventing us from doing the reforms? What are the concrete actions we should take to fix the?
My answer is we train people with what we're familiar with. All the tools that are out there, SNAP, ICE, GMT-SAR. Remember, these all came from ERS and VSAT era things. And Sentinel-1 metadata quality is what is enabling this. If I go try to do this in ERS and NVSAT, I'll still have to estimate a constant offset by doing cross-correlation and things. I think SAR sensors have improved, and I think that is what's enabling us to consider different methodology. We are still using the tools that were built for ERS and NVSAT. I think it's time to update or think about the processing paradigm a little differently.
Okay, last question.
When you make the geocoded SLCs with L-band data, do you do any ionosphere corrections?
We don't do anything. That's why it's a challenge for NISAR and all the L-band missions that I mentioned. I believe it should be similar to the ETAD corrections, that these expected range corrections should be provided with the data for this sort of mechanism to work.
Thanks.
Okay, thank you very much. Thank you to all the speakers. Marcus, you want to talk about the roundtable?
Yes, so to start the roundtable discussion, 1 minute, I'll get Nuno Miranda from the next room. I hope that the seed questions are on the drive. So. seed questions, this is not a comprehensive one, so if you have other questions to propose, please feel free. The first one is a generic one that is on the template for what does the community, and this community in particular, recommend that ESA will do in the short and medium term. So I've heard recommendations before for geocoded SLCs. I think it's a good one. Some people might disagree with that. So does anyone want to have a word? Any comments?
Oh, okay. From my point of view, I mean, with respect to the first question, of course, I mean, is to have access to the data, but also useful data, okay? I mean, to coherencies and everything. I won't give any recommendation into that. But one thing that would be very useful is to have, I mean, this is an old question, to have common data sets. I mean, the possibility to combine, I don't know, SAOCOM with ALOS, with Sentinel-1. I mean, I know this is very difficult to put everything together in one test site. And the other problem is to have ground truth for the data. I mean, if you are interested into some kind of applications, I mean, I think it's a huge amount of work, but it's worth to push into that direction, to have common data sets on the same area. Co-register is possible, I mean, to some point. Okay, so that would increase the possibility to extract information.
So you're suggesting that ESA should make a platform or some kind of processing.
I don't know how to
call it, where all this data would be available.
I don't know how to crystallize this, but the idea is to have common data sets. Okay, for instance, we have the Syncomap or other projects that we will present it in here with other data sets to have common data sets from different missions. I mean, because I think more or less we have a right to the limit with single technologies, single systems. So there is much more you can do with multiple combination fusion and these kind of things, okay? So, I mean, of course, you need these data sets for every single system, for wherever, but to make the effort to combine them or to have common data sets, I think it's worth the effort.
Right, yes. I mean, that sounds like that you are proposing some kind of a test site-based approach, because globally that gets quite expensive. I don't know.
Yeah, I know. Yeah, I know. But it is, at the end, it's worth to... I mean, in the future, we will have Sentinel-1 Roselle, so we need some data sets. At the moment, they are quite limited, so it's complex. But I think the only ones that can make that are space agencies.
Okay, thank you, Carlos. There's a mute button.
Let me just comment on that. There are already some attempts to that, Carlos. You know that it was also one of the things that we discussed in Polinsar. And there are already attempts in various sites. So for example, for agriculture or for ice, no? It's not still, say, a common platform or point where you could refer. After Polinsar, in fact, we started to collect all of these informations from different projects to see how we can combine it. So this is something that hopefully soon will be available for the community. But yeah, this is for sure something that everyone would appreciate.
There is another option between GSLC and Coreg SLC because here you're duplicating data volume between the L1 SLC. And for good co-registration, at least in C-band, if you are estimating correction parameters, constant range offset, constant timing offset, or some representation, if the space agency takes on the job of only estimating these correction factors, the user can generate the GSLC or the Coreg SLC with those and the original SLC. And these factors you compute once, they hardly take a few kilobytes because it's met in. So that is another option where you provide a correction service to enable co-registration, but not actually recreate the whole product suite.
My question is more dedicated to the PSINSAR tool. As we'll follow the STEMPS line, or we'll try to have own software, dedicated software for PSINSAR. Because we use STEMPS, we use that workflow that is from SNAP to STEMPS, but I miss the opportunity to join ascending and descending orbits, and different data sets. That is possible in different softwares, but not in STEMPS. So as we'll follow that line, or we try to have some independent tool?
Well, I mean, to me that sounds like that the community should step up and make such an open source tool, then those could be supported. I don't know if you're familiar with Pyrate. Personally, I'm not very familiar with it, but it's a fully open source, Python-based Australian software that does SBAS. But I mean, we specifically with Snap, we don't want to solve all the problems because there are too many problems. So that's why we facilitate communication with other tools, and then there are other communities that can then help you with stamps, for example. So my view is that ESA should not go into the PSI business. There's a lot of companies already doing that. But maybe, I don't know, if you, who's developing stamps? It's an, oh, there's a comment over there.
I have a comment about stamps. The last time we made a commit to it was in 2015. And so it's amazing to see so many people still using it. So related to that question, actually, is I have 3 points to make. A few years ago, from the comic community here in Leeds, actually, and wider UK, we released a statement to try and encourage people to move away from the master and slave terminology. And it's, again, amazing to hear that people are still using it. And I think that's a legacy of stamps, because we haven't gone back to do control find, control change in stamps, because none of us have the time. So please encourage people to move away from that terminology. Most of the software have, ICE and GMCR others. It is literally a matter of control, find, replace. And we can do that very easily, please. Second is, again, a legacy of stamps. Originally, the way it was written is this, what originally was called single master approach. Oh gosh. That wasn't me. This single reference approach. I mean, the Sentinel-1 time series is, is only getting, and some of these baselines can be at 5 years at least.
Can we switch the microphone?
Let's try.
Okay, so I'll just stand and shout. We all know the issues of temporal decorrelation. So it blows my mind that we are still using single reference interferometry. We ought to be moving away from that, particularly because the longer these time series get, the worse your results are going to be. And the third point was around Pyrate. Pyrate's even older than stamps. So it developed again in Leeds before even stamps was thought of. So again, from from MATLAB, which was then updated into Python recently by the Australian folks. So I think it's probably time we sort of develop more novel, more up-to-date time series methodologies.
Eric has a question here or comment?
Yeah, MinPy also works with the MinPy software, the Python code that uses SBAS, and it is
The microphone?
the MinPy software is a Python open source package that works well with Snap. So that's and that's being actively maintained. So that's a good alternative.
So would you recommend that we support MinPy from the Snap side? Is that needed?
I think it's very easy to put the Snap output into MinPy. It's just a matter of organizing the directories with a certain structure. So I think it would be very easy it wouldn't require much work.
Thank you for a very interesting session. You're asking recommendations, then if I may, then it's just one recommendation. Try to get the geocoded. It's working now. Okay, let's hope it's stable. Try to get. I will just say, drop the microphone. Just try, if possible, try to get the standard adapted as soon as you can at the first test products out. It always will be compromised. There always will be some users not happy. It's moving away from the native radar geometry and so on and so on. But eventually it will be an iterative process anyways. So even if it's imperfect at first, like the sooner you get the first standard adapted and first test products out, the sooner we get the ball rolling and the things going. Because inspired from the last presentation, I think it would really make a big impact of going out from the sandbox of the SAR community.
Thank you for the comment. I personally agree, but what the ESA's plans are with for Rosell, I believe the geocoded SLC is a standard product, and for Sentinel-1 next generation, I don't remember. I will have to check. There's a session tomorrow morning on future ESA missions. Tomorrow morning.
Thank you.
Yeah. Min.
I can shout. This I can. It's a comment regarding the second point, more of an end-user perspective. So about the need of harmonizing interfaces for accessing this different to the data different platforms. And I believe it's not really realistic to have similar interface at different level, because the use not the same at the regional, national, or European level, and the data are not designed the same way. But something that could be valuable would be to really have from EDMS to present a direct link to the national services, even in the web GIS tool if possible, to for example, use Zoom on the country, and the user can see, get a message saying, note that there is also a national service with different kind of projects, higher resolution, and such. I don't know if it's possible. Really nice.
Thank you for your comment. Any other comments? The floor is really yours. We don't have to stick with these 4 questions, but so anything related to, there was a talk about GPUs, anything GPU related, that any recommendations to the community, to ESA?
This one, yeah. Carlos?
I would like to make a comment on these GPUs, as you mentioned. I mean, it's more my comment is more general. It's about hardware, and it's something we are facing in Catalonia, for instance, is that you have a large need to have much powerful machines. And for some people, this is restricting the access to process the data. For instance, this is happening also in the world of data science. Only few companies in the world have the resources to process the data. So this is really, and it's becoming an entry barrier, especially for research groups, for institutions, for small institutions. So we have to be careful about that. We have to provide also that, for instance, in Catalonia, the government is trying to push to have a machine for all the companies, because a single spin-off cannot afford for that. So this is becoming, in this era where we are going to global applications and global processing, this is going to become an entry barrier for many actors. So we have to be careful of that. Also the storage, okay, because we are growing. And I mean, I'm from the university world, so I have my problems, but for spin-off companies, this is going to become for many small companies, this is going to become an entry barrier. In the same way of language models in artificial intelligence, okay? It's the same way. So ESA should take care of that needs too. Thank you.
Yeah, we're going to capture that. Carlos, thank you. Maybe the microphone works. Let's try.
Yeah, when we are submitting projects, we have more and more pressure to mention the cost of energy, of CO2 pollution when we produce our research, and it's rather hard to get the information on how much it costs to produce this data, and all these data are generated to observe the Earth or environment things. So one thing that could be perhaps good is to have an estimate by the ESA itself of how much it costs to launch the satellite, to generate the data, so that we can estimate our personal cost of research.
Right, so if I understood you correctly, you would want some kind of, because people do different processing using different software and different GPUs, CPUs.
Say, when I get my data,
yeah.
What was the cost of having this data?
You mean the total cost of satellite launchers?
Yeah, for example.
That's not very easy to calculate, but yeah.
Yeah, but the astronomy community has done the job.
Yeah.
Yeah, and for example, the launch is not a higher cost. It's preparing the thing before. So that's the attempt. It's not easy to do, but it's worth wondering.
No, I mean, of course the budgets are fully known. What's the Copernicus programmer's cost? So it's not an impossible figure to calculate, but there are several figures. So yeah, let's put it in the recommendations that this could be something to be looked at. But you want, as a taxpayer, you would like to know already before you download your product that how much.
Yeah, or at least have an insight of what's the cost of
yes.
of having this data.
I don't think there's anybody here in this room from a small SAR provider, because they might have an actual number that they could quote if it's not a secret. So how much is the cost per image for a small mission? So okay. I think we are close at the allotted time, so unless there are any last comments or anything else to add, I think we should join the welcome cocktail sponsored by the UK Space Agency. I think it's starting now.
Thank you.